Good morning, and thank you for attending the presentation. I'd first like to thank the organizing committee, Omar Al-Ayed, Mohammed, and Ibrahim for the kind invitation to speak today. My topic this morning will be new developments in the hydrometallurgical recovery of base, precious, and rare metals. I come from the University of British Columbia in Canada. Just a few comments about the university before I give my talk. The university is one of the largest universities in Canada, about 60,000 students in 2 campuses, many international students, including students from Jordan at the university, many degrees granted each year, and a very large budget and economic impact. So in terms of discussing hydrometallurgy and the recovery of different types of metals, I want to set the stage by, first of all, considering the demands for materials in the 21st century. Because as we know, the world around us is changing rapidly, and the need for materials is changing significantly. So life's changing rapidly. We have to decide what's important in terms of what we want to have, what do we desire, what comes next, and what materials do we require. We have a famous television program in North America called Family Feud, and it asks a question and then you have to guess the answer. So the question here is, what's indispensable in terms of materials for the 21st century? I saw an article online about how Googling has replaced the needle and thread. When we're often in conversation now, we don't use our minds, we use our phones to find the answer, because we're used to using technology to access information. So we have new skills that are often related to new technology, and new technology needs new materials. If we think about the changing field of automobiles, in 1967, when I was a young boy, the Corvette was the desirable car. Now it's the Tesla, different materials. I grew up using a slide rule, and of course now I have a MacBook, different materials. Old planes and new planes. Old planes, mostly aluminum and other lightweight materials. The Dreamliner, of course, is a carbon-based fuselage and advanced materials throughout, including lithium-ion batteries. In terms of power, we're seeing major changes in the way that we generate power for our society and for our industry. Historically, coal-fired power, and now, of course, solar and wind, a different requirement for materials. So how do these changes affect the supply chain for life in the 21st century? Well, historically, our emphasis has been on things like steel, concrete, aluminum, copper, nickel, lead, cobalt, chromium. And of course, currently, we still need all the historical materials. We never have made more steel or aluminum than we make currently, but we also need increasing amounts of other materials. And the other materials are drawn from the range of other base metals, precious metals, and rare metals. Perhaps one of the best examples of the changing face of materials is the material requirements for a smartphone. So if we take a typical smartphone and look at the different components, the screen, the battery, the electronics, and the casing, we can see very different materials being used in each of the different components. So for example, the screen is using indium tin oxides for the touch sensitivity of the screen. The battery is a lithium cobalt battery with other minor element components. The electronics, of course, still have copper, silver, gold. Some tantalum is there as well. Some rare earths are present: dysprosium, praseodymium, terbium, neodymium, gadolinium. These are there for the magnetic aspects of the smartphone. And then the casing contains lightweight metals, including magnesium. So different elements all coming together in a component of advanced technology, changing materials requirements. If we look at some of the increases in demands for some of the newer elements that we're using in society, we can look first at lithium. So lithium is being highly sought after, of course, for battery making materials with very large increases. The curve is actually getting steeper in terms of the projection. meaning that we're being constrained in terms of our lithium supply. Rare earth supply, you can see China is the dominant producer of rare earths. They consider rare earths like the Middle East considers oil and energy materials as part of their birthright. The supply is mostly from China, but increasingly outside of China as the demand continues to rise. As I said, some of the historical metals are still being used in ever-increasing amounts. The production of copper now is close to 20 million tons per year globally, and aluminum is close to 50 million tons per year globally, showing very large increases in many sectors. When we look at indium, again for the smartphone screens and for advanced electronics, you can see roughly a 10.5% annual growth from 1982 to present. Still only about 700 tons per year, but of course a very valuable material and very important for certain segments of our technology. So the question I want to look at today is how do we meet the material demands for life in the 21st century and beyond? And I want to look first at sort of who contributes to the material supply chain. We have geologists, of course, who are very effective at where we find materials in nature. We have mining engineers who will help us safely extract raw materials from the earth. We have metallurgists and material engineers, of which I'm one, who will teach us how to process the materials and separate them. Chemical engineers, of course, are very complementary to metallurgy and materials engineering disciplines. I have two children who are chemical engineers, both working in the raw material areas. Waste management, I know in Jordan there's a move to recycle many of the industrial wastes that are present. So we want to reduce, reuse, and recycle. We want to learn how to manufacture in order to incorporate materials into products and add value along the way. And of course, engineers, including chemical engineers, are an important part of the future. So what is hydrometallurgy? Well, hydrometallurgy, although it has the term metallurgy in it, is really kind of a discipline of chemical engineering. And it's a very important part of the materials supply chain. What is it? Well, it's basically processing of metals in water-based systems. And the three different steps that we usually employ in hydrometallurgy are primary extraction, which is to recover the metal into the water-based solution, separation of the metal of interest away from undesirable metals, and then finally recovery of a metal-containing product. So it's really a hybrid, again, between traditional metallurgy and chemical engineering. Some large-scale examples that are probably familiar to many of you from the chemical field: the Bayer process for alumina. This is a process that takes bauxite ores from the mine and treats them at high temperature and pressure in an alkali solution to separate the aluminum away from iron in particular, iron and silica. And the final product from the Bayer process is alumina, which then goes off to a smelter for reduction to aluminum metal. There's the flow sheet, and then here's a picture of a large-scale alumina plant in Jamaica. You can see the red color of the earth around the plant. This would be indicative of the red mud product coming from the Bayer facility. In terms of metals that I would work with more commonly, copper. We have the traditional copper heap leach, solvent extraction, and electrowinning process. This is a process that's widely used in South America, United States, Australia, Asia. And it starts with a pile of rocks in the top left-hand corner. Try to use the mouse here to point that. So you see a pile of rocks which is being irrigated with an acid solution. The acid is percolating through the rocks and dissolving copper, which is recovered into a pond. The copper-bearing solution then goes through 2 stages of solvent extraction. So it's loaded on an organic solution, and then it's stripped using a stronger acid solution to make a concentrated copper solution, which then goes to electrolysis. The electrolysis then produces copper as plates of copper cathodes, which are used as the product of sale from the plant. So here's a picture of a large heap leach in Chile. You can see the workers are preparing a plastic pad which prevents the solution from being lost into the earth. And in the distance, you can see a stacking system, which is placing the ore on top of the pad. When the pad is finished, they then use drippers. It's like a farming operation, drippers on top of the pad to sprinkle sulfuric acid, which goes down through the rocks and dissolves copper. So the solution that's being collected in the ditches is a copper-bearing acid solution. That then advances to solvent extraction and electrowinning. These are solvent extraction mixer settlers in the distance, which are contacting the copper leachate from the heap leach with an organic chemical that's selective for copper and transferring it to a solution for electrowinning. And then in the electrowinning facility, the purified concentrated copper sulfate solution is electrolyzed to produce copper metal as a final product. Another example of hydrometallurgy, which is becoming increasingly important, is lithium recovery from Solarz. And I understand this is mostly focused in South America, in Chile, Argentina, and Bolivia, but there are other Solarz around the world that are also important in this respect. You can see that on the left-hand side, the salt solutions are being recovered from brine wells and then going through a whole series of different ponds, which selectively precipitates and separates different components of the salt, the last part of which is the lithium concentration pond, from which we then draw the lithium products that go into the batteries. So the lithium solutions coming out the far right-hand side go through the lithium separation plant and become lithium hydroxide, lithium carbonate, and lithium chloride, which of course enter into the battery making production. And here's an example again from a couple of pictures from the Rockwood website. Rockwood's one of the major producers of lithium. You can see two facilities, one in Chile and one in Nevada in the United States. And you can see the very large ponds that are used for evaporation of the salt solutions. So in terms of my own interest and background, I thought I would talk about some of the examples of aspects of technology that we've been working on at the university and with industrial partners in the three segments of base metals, precious metals, and rare metals. In terms of base metals, I have two examples from the copper field. One is a project in Southeast Asia, in Sipon, in the country of Laos, a technology called Galvanox, which was developed by one of my colleagues at the university, and also a process for lead recovery, which is now being commercialized by a company called Incor. On the precious metal example side, we have two examples, thiosulfate leaching of gold and also the Platzol process. Thiosulfate is being developed as an alternative to use of cyanide for recovery of gold from natural ores, and the Platzol process is used to recover base and precious metals from complex ores. And then on the rare metal side, I've got an example of a project in Canada that's trying to recover rare earth materials to develop supply outside of China, and also the work on lithium recovery by a group called Tenova Advanced Technologies. So in terms of base metals, I'll first start with the Sipon project. Sipon is a project located in a remote area of eastern Laos in Southeast Asia, and it's got very little infrastructure support locally. The copper minerals are predominantly chalcocite, and the ore contains a lot of clay. When the feasibility study for the project was completed, there was about 700,000 tons of copper at a very high grade, about 5.1% copper. And the plant that was developed has been recovering from the start 60,000 tons per year of copper at an overall recovery of 90%. And the plant started in 2005, so it's been running for about 12 years. So here's a picture of the Sipon map. So Laos is a country that's positioned between Vietnam to the east and Thailand to the west. China's to the north and Cambodia's to the south. When we started to look at this ore body, we found that Whole ore leaching was effective at leaching copper from copper sulfides using a ferric-ferrous oxidation system. The trouble we had with the ore is that because of the clay present, the ore consumes a lot of acid, and the cost of acid in Laos is quite high. So in order to make the project economic, we had to determine a way to make our own chemicals in Laos, and this involved making ferric sulfate sulfuric acid solutions by recovering sulfur and pyrites from the leach residues by flotation and oxidizing those materials in a high-pressure autoclave. So the process block flow sheet is shown here. You can see in the center of the figure, you have the main flow of the ore from crushing, milling. There's some heat exchange to heat the ore, atmospheric leaching, heat exchange for cooling the ore, further cooling through a cooling tower, and then clarification to recover the copper leachate, which goes on to solvent extraction and electrowinning to make the copper cathode. The slurry is then washed, first with raffinate from the solvent extraction, and then with water. And then the innovative part was the use of flotation at the end of the circuit in order to recover elemental sulfur and pyrites. The pyrites and elemental sulfur are directed to a high temperature autoclave where they're oxidized with oxygen in order to produce sulfuric acid and ferric sulfate. The sulfuric acid and ferric sulfate are then added to the main leaching circuit in order to meet the reagent demands for the process. So here's some of the chemistry. In the atmospheric leaching for the ore treatment, the copper minerals are oxidized by ferric sulfate, and we get some ferric regeneration by introduction of molecular oxygen. The flotation recovers the pyrite, elemental sulfur, and also any copper minerals that are not leached in the atmospheric leach, and these are then sent to the autoclave, which operates at 220 degrees Celsius for 1 hour. Of course, the pressure is around 30 atmospheres, and this converts the pyrite and sulfur to basic iron sulfates and sulfuric acid. Very importantly, any copper that's not been leached in the main circuit that can be floated with the pyrite and the sulfur can also be recovered and leached in the autoclave. This shows on the left-hand side the autoclave feed, and you can see in red the two major phases are sulfur and pyrite, but there are some minor copper minerals like covalite, energite, tetrahedrite, and chalcopyrite. And then on the right-hand side, you see the discharge. The sulfur and the pyrite are basically fully oxidized. The copper minerals are extracted, and we're left with this product called basic iron sulfate in the autoclave discharge. So the reactions are oxidation, and in the case of basic iron sulfates, precipitation. So the red equation shows the formation of basic iron sulfates at high temperature in the autoclave. After the autoclave, the residue is allowed to condition at 95 degrees C for a number of hours, and this allows the basic iron sulfates to redissolve and form a very strong ferric sulfate solution before transfer to the atmospheric leach. So the post-autoclave conditioning step forms a very strong ferric sulfate solution, which is then used to attack the copper minerals and create leaching conditions. So at CEPON, the challenge that was presented in development was to find inexpensive sources of acid and reagents for treatment of a highly leachable copper ore, and this resulted in the development of the high-temperature autoclave to treat the flotation concentrate. And this has allowed CEPON to recover copper now for the last 12 years at a very high rate. And here's a picture of the plant in Laos. It's in the jungle, so it's a very tropical environment. And you can see it's also got some Chinese symbols because the current owner is a Chinese group. The mine is on the slope at the top. The copper ROM pad is where the run-of-mine ore is placed from the mine. Crushing and grinding is the feed preparation of the ore. This is the leaching area. And then you can see the thickeners, which are used to do the solid-liquid separation and washing. The leachate from recovered from the thickeners goes to solvent extraction and electrowinning. You can maybe make out a little bit of steam in the picture just shown here. This is the steam coming from the autoclave plant, and the autoclave plant is receiving oxygen from the oxygen plant just down to the bottom left-hand side. Okay, a second example of a development in base metals is the development of a process called the Galvanox process by one of my colleagues at the University of British Columbia named David Dixon, and two of his students, Elaine Chalombo and Ghazaleh Nazari. The process is to leach chalcopyrite, which is a common problem in the field of hydrometallurgy, how to compete with high temperature metallurgy for the recovery of metals. So the Galvanox process was developed as an atmospheric leach without bacteria, just containing sulfate, no fine grinding, produces high levels of elemental sulfur with low oxygen demand, no surfactants, selective for chalcopyrite over pyrite, fairly fast copper recovery, less than 12 hours, fully compatible with conventional solvent extraction and electrowinning, and conventional materials of construction. So how does it work? Well, Galvanox is an attempt to use electrochemistry to aid in the decomposition of the mineral chalcopyrite. So Galvanox takes advantage of the galvanic effects that occur between chalcopyrite and pyrite. Chalcopyrite is a semiconductor, and we believe it corrodes electrochemically in oxidizing solutions. So we write the overall reaction for leaching. Chalcopyrite plus ferric sulfate goes to copper sulfate, ferrous sulfate, and elemental sulfur. But we can think about this reaction as having two components. One, an anodic process, which is the corrosion of chalcopyrite, and one, a cathodic process, which is the reduction of ferric to ferrous. So if we think of a picture, electric circuit picture, if you will, that shows what happens during what we call unassisted chalcopyrite leaching, we see the chalcopyrite mineral is corroding on the left-hand side at the anodic site with the release of copper ions, iron ions, and formation of elemental sulfur. The electrons from the anodic site then can pass through the semiconductor and go to a cathodic site where ferric is being reduced to ferrous. When we do experiments of this type to try to study this reaction, this is what we normally find. We get some leaching of copper, but after an extended period of time, we find there's unreacted chalcopyrite in the center, there's a sulfur layer around the outside, and the leaching stops. In the corrosion terminology, the reaction is passivated. So in terms of development of Galvanox, what my colleague studied was the passivation phenomena and trying to understand how to overcome it. And essentially they found that the passivation is probably taking place on the cathodic reaction, which is the ferric reduction reaction. And by putting pyrite, which is the iron sulfide mineral in the system, they found it was possible to catalyze the pyrite, or catalyze the cathodic process. And of course, the pyrite is considered inert and can be recycled. So in terms of, whoops, lost something here. Oh, there we go. In terms of the electric circle with pyrite present, you can see that pyrite takes the role of being the preferred site for the cathodic process. So we now have contact between chalcopyrite and pyrite, but the cathodic process occurs on the pyrite. The electrons move from the chalcopyrite to the pyrite, and chalcopyrite continues to dissolve anodically. So now when we do studies of this type, field A on the left-hand side is a sample taken partway through the experiment, so the leaching was not yet finished, but you can see now a very thick layer of sulfur surrounding the unreacted chalcopyrite. The leaching is still continuing, but we stopped the reaction prematurely. On the right-hand side, on the B frame, you can see the products at the end. So now we have a particle of elemental sulfur that used to be a particle of chalcopyrite. many particles of elemental sulfur, and then many other particles of pyrite, which is not reacted. It's present simply as a catalyst in the system to aid in the electrochemical breakdown of the chalcopyrite. So in terms of completing the process, we want to do chalcopyrite leaching under Galvanox conditions with ferric sulfate. We have to regenerate ferrous to ferric using oxygen. So the overall leaching reaction is actually an oxygen leach, where the oxygen is regenerating ferric to allow the oxidation of chalcopyrite to continue. The copper sulfate is treated by SXEW again, and the iron sulfates are treated by precipitation to reject an iron waste product. Okay, so here's the iron hydrolysis reaction, copper electrowinning, and if you were to add all the reactions together, you find that chalcopyrite enters the process, oxygen is added for leaching, copper metal comes out, elemental sulfur is formed, oxygen evolves in electric winning, and iron oxides are produced as the waste product. In terms of the lab work that's been done, these are all done in small-scale, carefully controlled reactors where the temperature, the potential, the pH, and so on can all be controlled. And here's a typical experiment that shows what happens when you try to leach a chalcopyrite concentrate containing about 35% copper. If you leach it with no pyrite addition, you get the lower curve. So you can see after 24 hours, the leaching has stopped at about 50% copper. With the introduction of increasing amounts of pyrite as a catalyst under Galvanox conditions, the leaching quickly approaches completion within about 8 to 12 hours. So it shows the efficiency of the catalytic system. Here's another concentrate, somewhat lower grade, 23% copper. You can see that 20% copper is all that leaches directly, but with the addition of pyrite again, within 8 hours we're approaching 100% extraction of the copper. Here's one that has a bit different behavior. It keeps leaching, but it's taking a long time to get to the end. Whoops. But again, with pyrite addition, there's a benefit. Another one similar. And then finally, this is an example of a chalcopyrite bulk concentrate recovered by flotation. In this case, there was already some pyrite that was floated with the chalcopyrite, and you can see the mixture is catalytic without any requirement for extra pyrite addition. So in terms of studying the Galvanox process, some of the key questions that have been asked are all pyrites equal in terms of their catalytic abilities? The answer to that is no. Can pyrite be improved in catalytic ability? The answer is yes, and the key element that makes one pyrite better than the other is having a little bit of silver on the surface. Third question is, how do you have galvanic contact when the chalcopyrite gets coated by elemental sulfur, which is a natural insulator? This has an interesting answer. And what about other copper minerals besides chalcopyrite? There's a lot of interest globally now in the copper arsenic minerals, which are found widely in nature. The mineral is called energite. Can we adapt Galvanox to treatment of these minerals? And the answer is yes. We can leach other minerals besides chalcopyrite with Galvanox. So one of the PhD students at the university did work on trying to understand the different types of pyrite and improving bad pyrite and making it into good pyrite. So she investigated the kinetics of chalcopyrite leaching and especially looked at silver treatment of pyrites to make them more catalytic. So here's her starting experiment, which is the unassisted chalcopyrite leaching. So in 90 hours, roughly 42% copper leaching. She then took some pyrites and did Galvanox experiments, and you can see that the results aren't nearly as good as the ones that we saw previously. We were leaching in sort of 8 to 12 hours. The time frame here is 100 hours. The ratio is 6 to 1 pyrite to chalcopyrite, and in a couple of cases we're getting eventually to 100%, but it's very slow. And in one case, we've actually done worse than the uncatalyzed system, finishing at less than 40% copper extraction in 100 hours. So these pyrites, these 3 different pyrites, were then treated with 100 parts per million of silver, just by mixing the pyrite with a silver nitrate solution and allowing the silver to precipitate on the surface of the pyrite. Now the 3 pyrites all behave very similarly. They all give a very fast reaction, and now within 10 hours, we're getting close to 100% copper leaching. So the difference between the bad pyrites and the good pyrites appears to be the presence of silver on the surface of the pyrite. If we put the different experiments all in the same time frame plot, you can see that 3 bad pyrites have become 3 good pyrites with the addition of small amounts of silver. If we recycle the pyrites can continue to be catalytic. You can see the recycling shown here on the left. Sorry, this is the fresh pyrite, and this is the recycled pyrite. So the recycled pyrite still has catalytic ability. We can also work at higher percent solids, which is important for an industrial process. This would produce a solution of 70 gram per liter copper at 80 degrees Celsius. And if we do silver catalyzed leaching with the Galvanox process, which is the pyrite catalyzed leaching, the Galvanox is the orange-colored symbols, and the silver catalyzed leaching of chalcopyrite is the blue symbols. You can see that the initial condition is better, and then when we recycle the pyrite, we can use it again, whereas the recycle of the residue from the silver catalyzed leaching is not effective for leaching of copper. What about this problem of insulation? So in terms of the electric circuit, the electrons have to move from the chalcopyrite to the pyrite, and they have to go through this elemental sulfur layer that grows around the surface of the dissolving chalcopyrite particle. Well, it turns out that the silver that's present in the system plays a very important role in promoting conductivity of the sulfur layer. So if we look at the sulfur conductivity with silver present in the system, whoops, went too fast there. With silver present in the system, we've got a conductivity or a resistivity of 1 to 10 to the 7th, and without silver, it's almost 4 orders of magnitude more resistive. So the silver seems to make the pyrite more catalytic, and it also has the benefit, oops, not sure what I'm touching here. Okay, it also has the benefit of making the sulfur layer more conductive and allowing the electric circuit to maintain the current density that's required for leaching. This shows the measured resistivity of sulfur as a function of the silver content of the sulfur. So even a few ppms, a few parts per million of silver in sulfur dramatically increase the conductivity and allow that electric circuit to continue. We also looked at other catalysts besides silver. Turns out that mercury also has a beneficial role in the Galvanox system. Of course, the toxicity of mercury makes it less desirable as an additive, but of course the science says it's interesting that another element can also have the same benefit. So in terms of Galvanox, a process was developed for chalcopyrite leaching that used small amounts of silver to pyrite. The calculation was about 60 milligrams of silver as a makeup required per kilogram of copper recovered. The acceleration of chalcopyrite leaching was due to the galvanic interaction between the minerals. Pyrite is critical and provides a surface for ferric reduction, and silver seems to have a critical role in terms of decreasing resistivity of the sulfur layer and also increasing the catalytic properties of the pyrite and the rate of ferric reduction to ferrous on the surface of the pyrite. Okay, a third example from the base metal field is the recovery of lead from natural ores. And here I want to talk about the in-core lead process. So lead is normally recovered from nature or from natural materials using high temperature pyrometallurgy. So at the mine, a lead sulfide concentrate is floated. The lead sulfide is then roasted or smelted. This produces SO2, and of course can also produce dusts and gases that contain lead. You can also treat oxidized minerals or oxidized materials using pyrometallurgy. If you treat oxidized materials, there's no fuel, so you have to incur a lot of expense for fuels and heat. Hydrometallurgy is a great alternative for lead because, of course, it's low temperature. We prevent the environmental problems from the smelting process. We can treat lower grade or more complex materials, and we could perhaps treat oxidized minerals or secondary lead resources. In terms of the thermodynamics of the lead system, this shows that if you've got lead minerals in nature, this is a lead carbonate type mineral, you can leach it by going to lower pH or to higher pH. This mineral is found at a mine in Australia, the Peru Station mine in Western Australia, where the mineral sericite, lead carbonate, is the predominant mineral. So what did we look at in terms of hydrometallurgy for lead? Well, we wanted to find an acid that could leach lead with high solubility for lead. We wanted to overcome any difficulties in downstream processes and wanted to have a much lower environmental footprint. So we started to work with an acid called methane sulfonic acid. It's regarded as a green acid. Not sure exactly what the word green means here, but it's more favorable than some other chemical products. It has high solubility for heavy metals. You can see that the solubility for lead in methane sulfonates is more than a kilogram of lead per liter of solution. It's got high conductivity. We need higher conductivity here. There we go. High conductivity. It's non-oxidizing and has stable thermodynamics. It's odorless, low toxicity and low corrosivity, and it's biodegradable and recyclable. So what is it? Well, it's like sulfuric acid, except one of the OH groups has become CH3. So it's the simplest organic sulfonic acid. It's got a pKa similar to sulfuric acid, and it's being produced industrially now in greater and greater quantities. And this just shows the vapor pressure and the pKa for the different acids. And you can see that sulfuric acid and methane sulfonic acid have very similar vapor pressures and pKa values. So what do we do with the acid? Well, the acid has a high solubility for lead. So we take our concentrate from the mine, the sericite concentrate, we leach it with the acid, we filter and wash the leachate, we go through some purification, and then on to electrowinning. And that allows us to produce lead metal directly. In the ore in Australia, there is a little bit of lead sulfate. So we have a separate circuit that deals with the small amount of lead sulfate, first by desulfurization, and then by another methane sulfonic acid leach. We've also adapted the chemistry to treat galena concentrates, lead sulfide concentrates, again using the ferric system in the methane sulfonate system. So there's the oxidized lead mineral leaching, and there's the lead sulfide mineral leaching. There's the desulfurization chemistry. We can use sodium carbonate or sodium hydroxide, but it allows us to convert the lead to the soluble form, lead carbonate or lead hydroxide. The reaction is extremely fast. So the scale here is seconds. So this represents 600 seconds is 10 minutes. You can see that the leaching is basically complete within 10 minutes, as long as we have enough mixing in the system. In the galena leach, you can see it's also complete in about 10 minutes. So very rapid leaching with high solubility. Temperature doesn't make a huge difference to the sericite leach. It makes some difference to the galena leach. Particle size, even coarser particles are leached very quickly, all within 10 minutes for the cerussite and roughly 45 minutes for the galena. Effective free acid, very small effect. If you start to run out of acid, the leach will slow down a little bit for the cerussite, but the galena is quite effective over a wide range. And if you run at higher pulp density, you can see that we can easily make solutions of more than 100 gram per liter lead by leaching the cerussite. When we combine the two steps of primary leaching and then the desulfurization leach, you can see the primary leaching recovers about 85% of the lead, and with the desulfurization leach, we're getting a total recovery of around 98% from the ore. This is going to allow, we're doing a study now for the mine in Australia, this will allow the mine in Australia to make lead right at the site and not have to ship their concentrate overseas to a lead smelter. We can then electrowin lead. The nice thing about lead is it has a very high molecular weight, so the energy requirement per kilogram of lead is quite low. It's only about 0.53 kilowatt hours per kilogram of lead to plate lead from solution. So methane sulfonic acid is very suitable for treating lead concentrates. The kinetics are very fast. Total recoveries approach 100%. We can electrowin the lead as a smooth deposit using different additives like calcium lignin sulfonate. And you can operate the lead electrowinning under a wide range of conditions. Current efficiency and energy consumption are very respectable. And currently we're doing a feasibility study with the mine owner in Australia with the goal of trying to build the first lead refinery of this type in Australia starting next year. What about precious metals? These are far more interesting than copper and lead. Well, two major developments to highlight here. One has been commercialized and one is still being commercialized. The large Canadian mining company Barrick Gold has now commercialized the use of thiosulfate as a replacement for cyanide for gold leaching. So thiosulfate is used as a replacement for cyanide to extract gold from oxidized residues coming from autoclaves. The reason for the use of thiosulfate at the site in the US, the Goldstrike site in the US, is that when you form a complex between thiosulfate and gold, it doesn't absorb on carbon. Turns out the ores in the Goldstrike mine contain natural carbon, and if you try to leach with cyanide, the gold cyanide complex is reabsorbed back into the natural carbon in the ore. So the thiosulfate overcomes that limitation and allows the gold to be recovered without what they call preg robbing of the gold. So they recover the gold thiosulfate complex on a resin using a resin leaching process, and then they elute the resin and electrolyze the gold to produce the gold metal. So here's a picture of the industrial site in Nevada. This is the Barrick Goldstrike plant. So the old parts are autoclaves, which are used to oxidize pyrites in the ore that contain the gold. The resin leach process is where they use thiosulfate to attack the gold that's available after the autoclave treatment. The recovered gold is then eluted and electrolyzed to make gold metal in the elution facility. And then the two other bits that are new are they actually had to make their own plant to make thiosulfate at the gold mine because the demand for thiosulfate was so great. And they also have what they call a reagent recycle area where they take some of the dilute solutions from the plant and they use reverse osmosis to concentrate the reagents for recycle. And this allows them to minimize the cost of reagents for the gold leaching. They're now recovering about 400,000 ounces of gold per year using this technology at this plant in Nevada. Second example that relates to precious metals is the development of what's called the Platzol process. So Platzol was developed as kind of a simple process for one-step extraction of both base and precious metals. It was invented at Lakefield Research in Canada, and it's gone through a series of test programs using batch testing and continuous testing to prove the merits of the process. And you can see that we get very high levels of base metal recovery and also precious metal recovery using Platzol. The target for the development of the technology was a mine in the United States called NorthMet, which is owned by a company called Polymet Mining. Polymet Mining has the name Polymet because there's many different metals contained in the ore at NorthMet. You can see that it's got copper, nickel, cobalt, of course iron and sulfur are there. Whoops. And then there's gold, platinum, and palladium also in the ore. If you try to concentrate the material, you can make a bulk concentrate that contains the copper, nickel, cobalt, platinum, palladium, and gold, but the material is very complex, and smelters don't usually like complex materials, so we had to develop our own technology for recovery of metals from the concentrate. So we found that when we do a high temperature autoclave treatment of the ore, if we do it under conventional conditions, we get very high extraction of the metals, the base metals, but generally low extraction of the precious metals. And that's because the precious metals aren't soluble. Palladium is a little bit soluble, but platinum and gold are not soluble at high temperature. If we use the Platzol conditions, we once again get very high extraction of the base metals, but now our precious metals are also extracted. And what's the difference? Well, the Platzol process uses small amounts of salt, sodium chloride, or perhaps hydrochloric acid, in order to create the conditions necessary for precious metal extraction. So under Platzol conditions, all the metals are recovered. The process involves addition of chlorides to the high temperature oxidation, which promotes the precious metal recovery. The PGMs, copper, nickel, and cobalt, can then be selectively recovered. And the following slides show some of the chemistry. So when you go into a high temperature autoclave with oxygen, the minerals are oxidized completely. So copper iron sulfides become copper sulfate, hematite, and acid. Pyrites become hematite and acid. Pyrrhotite, hematite, and acid. Nickel is nickel sulfate. And we can also get some of these basic iron sulfates forming once again. When we put some form of salt in the autoclave, we already have acid from the oxidation of sulfur, so we can imagine that we have HCl present. So the metal, the oxygen, and the HCl react together to give us the metal dissolved species, in this case the auric chloride, or the platinum chloride, or the palladium chloride. This occurs readily at temperatures of 220 to 230 degrees C and produces a barren solid which can be washed and discarded. So this shows the conditions necessary for extraction of the gold: high temperature, low pH, and high oxidation potential. For palladium, low pH and high oxidation potential. And for platinum, low pH and high oxidation potential. We did many different tests in the bench scale showing the effect of different conditions. The one that's most interesting in this table probably is the lower temperature one, 200 degrees Celsius. Oh, that didn't turn out very well. But I'll just say that the test number 5 produced very low recovery of gold, platinum, and palladium, because at 200 degrees Celsius the oxidation wasn't complete. We didn't get to that high oxidation condition in the top of the thermodynamic diagrams. How do you recover the metals from the leachate? Well, copper can be recovered by SX-EW and nickel by precipitation. The precious metals can be precipitated. In this case, they were precipitated with sodium hydrosulfide, which drops the potential of the system and makes a sludge that carries the gold, platinum, and palladium. You can see the grade now is many hundreds of grams per ton, so very valuable sludge coming from the precipitation process. So there's the overall technology. So the bulk concentrate is reground, goes through Platzol. You recover a precious metal precipitate, recover copper, and then the bleed goes out to nickel and cobalt recovery. We've tested this on many different concentrates. The paper has a whole bunch of different concentrate grades, but generally the recovery is similar to what we saw for the North Met, and especially for the precious metals, it generally is over 90% directly. We've also tested the chemistry for copper-gold concentrates, refractory gold, precious metal mats, platinum-containing laterites, and automobile catalysts. You can see the copper-gold concentrates. So directly in one step recovering almost 100% of the copper and 96% of the gold, and no use of cyanide. Here's a refractory gold ore concentrate. Again, 96% gold, 99.5% silver, no cyanide. I do have an example of rare metals as well, which I think in terms of my time I'm going to have to probably skip to allow a few minutes for questions. But we do have a large deposit of rare earths in the eastern part of Canada, which we're working on development of recovery, and hope to have a mine in the next number of years for recovery of rare earths in Canada. So in conclusion, I just want to emphasize that the world needs more materials and more variety of materials. Hydrometallurgy is a wonderful discipline for the use of water-based chemistry to recover metals from all different raw material sources. The world needs more base metals, more precious metals, more rare metals, and hydrometallurgy can play a key role in providing the supply chain for life in the 21st century. So thank you very much for your attention this morning.
Thank you very much, Professor David Dresinger, for this highly valuable presentation. It took me back really to 2001 when I did many things on chalcopyrite leaching. Even we applied microwave energy to enhance the leachability of chalcopyrite using ferric sulfate and ferric chloride. But I ended up with saying there is a strong passivation layer that we can't go even further. But with your new process and the catalytic effect of pyrite, the problem I think is solved now. And thank you again for hearing about the new acid, which is the methane sulfonic acid, which has a very high solubility for many minerals and metals. Really very exciting presentation and very exciting information. I think we have very limited time, so we may handle 1 or 2 questions at max.
Thank you for this good, informative lecture. But I would like to hear about something about the cost of the different methods for the extraction of these metals. You mentioned many methods for recovery or extraction of the same metal, but no comparison between the cost. This is a very important parameter.
So the question was, how do you compare the cost between the different methods? And the answer to that, of course, is you have to do engineering studies to make sure you understand the cost. So for the CPON project I talked about as an example, the cost of production is around 80 cents per pound of copper, going from the mine through to metallic copper. That was based on the testing that took place and the engineering study. And now, of course, the plant's been operating for more than 10 years. So there's a good database of cost from the process. For the lead technology, which is one that I'm currently studying the economics of, we find that the cost is maybe $300 to $400 per ton for lead, less than the cost of sending the concentrate to the smelter. So we're using the cost saving in the technology to justify the building of a refinery in Australia in order to lower the cost we can afford to build a refinery in Australia. So for every one of these examples, there's always an engineering study sitting beside, which is trying to make sure we understand the competitive nature of the technology before we implement it. Yeah?
One last question.
Okay.
Thank you very much. My question is it true that the US went into Afghanistan because of the large reserves of lithium there?
I don't know anything about lithium in Afghanistan. There's very large reserves of
One of
lithium.
the reasons why the US went into war into Afghanistan due to the large reserves of lithium. Is it true? It's something I've heard in a talk show.
I have no knowledge of that, and of course I'm from Canada, not the US, so I can't tell you that.
Thank you very much.
Okay.
I received an order from the chair of the conference to open for more questions. So, sir.
Thank you, Professor, for this scientific paper. My name is Engineer Mohammed Al-Momen. In nuclear techniques, in this full application, you mentioned about cobalt. And cobalt is used for irradiation in wastewater, municipal wastewater treatment, industrial wastewater treatment. My specific question for development, source of cobalt as an isotope, environmental isotopes used for treatment. Treatment is very important in wastewater, industrial wastewater, to be used almost for irrigation, water supply, and others. So, extraction of this isotope globally. Thank you.
So I think that if I understood the question correctly, it was about the extraction of cobalt isotope in order to use it for wastewater treatment. So you're talking about the radioactive isotopes of cobalt, or cobalt 60? Well, I don't think cobalt 60 occurs in nature, but I think it occurs in radioactive waste from nuclear reactors. So I think it's recovered as a special isotope from radioactive waste, not from natural materials. So I think the answer to that probably falls more in the nuclear field than in the chemical or extraction field. But certainly cobalt separation away from other metals is commonly applied in hydrometallurgy. So maybe I can talk to you specifically about that afterwards, but yeah, okay?
I have a specific question. I actually went down to a mine and took samples and did the analysis. It contains iron, zirconium, titanium, and wolfram. I want to separate them, okay? From iron, I want to proceed to iron oxide pigments, and I want to separate zirconium from other metals to go to nanotechnology or nanogrinders. I know the process to do this job. If yes, please. If no, can you cooperate? Thank you.
Okay. So I would say I don't have any process right away that separates iron, zirconium, hafnium, and wolfram, which is tungsten, right? Tungsten mineral? Yeah, but I'm sure that there's a chemistry that can be developed to do that separation. Some combination of physical and chemical separation should be available to make that separation of the different products. So I don't have an immediate answer for you. I can't draw a flow sheet right away, but I'm sure we could talk afterwards and maybe there's some collaboration. Yeah. Okay? Thank you.
Professor Ising, I would like to ask again a specific question about the energy consumption. Here you mentioned this good process or optimized process for producing cobalt and other rare materials. metals, especially copper. Copper, I think, some colleagues from the Ministry of Energy and Mineral Resources can confirm this amount. But if we're going to apply this process here in Jordan, what about the energy consumption? Because the energy consumption of the energy factor is a significant, let's say, parameter for this process, especially here in Jordan.
Yeah.
I would like to have some figures about the process, for example, as a reference plant you have mentioned here, this plant in Laos with 60,000 tons per annum. Similar process if we're going, or similar plant if we're going to establish it here in Jordan, the energy consumption. Thank you so much.
Okay. So with copper recovery, the two major components of energy consumption are the energy required for mining and grinding, and also for the stirring of the leaching reactors. And then the major consumption is the electrolysis reaction. So the normal number for energy consumption for copper is around 3,000 kilowatt hours per ton of copper. Okay, and of course that will vary depending on the type of ore and the location and the type of process used, but 3,000 is a good starting point. So with respect to electrowinning, electrowinning itself is about 2,000 kilowatt hours per ton of copper. So 2,000, which is 2/3, is for electrolysis. 1,000 is for all the other components of the energy usage. This is electrical energy usage, okay? So the mine in Laos would have a consumption of about 3,000 kilowatt hours per ton of copper, which is not so bad in terms of cost.
Okay, thank you once again, Professor David Dresinger, for this valuable presentation.
The effect of mixing on CAO catalyzed biodiesel production process. Introduction. Biodiesel is the alternative biodiesel that can be used on its own or mixed with petroleum diesel fuel in ratios for conventional engine without any further modifications. Transesterification, also called alcoholysis, is the reaction of an oil or fat as a triglyceride with an alcohol, usually methanol, in the presence or not a catalyst, to form a fatty acid, methyl ester, and the glycerol, with the following simple question. 1 mole of triglyceride with 2 moles methanol gives 3 fatty acid methyl ester and 1 mole of glycerol. There are many processes for biodiesel production. Homogeneous process is the most used process. Our research directed to using heterogeneous catalyst for the following features. The catalyst can be reused. There is no or very less amount of wastewater produced during the process. Separation of biodiesel from glycerol is much easier, non-corrosive, and environmentally safe, and present fewer disposal problems. Disadvantage of heterogeneous catalyst is the long time of reaction due to poor mass transfer between reactants. Our previous work on conventional calcium chloride for catalyst for this process, we found some variation on contradiction in the literature on the use of CAO catalyst. And limited research works was done on the effect of mixing, especially for heterogeneous catalyzed process. The objectives: to design experiments to identify the effect of 3 operating variables, namely agitation speed, CaO catalyzed content, reaction time, on biodiesel yield, using a statistical method for planing experiments, response surface methodology, and central composite design to obtain optimum operating condition for maximum biodiesel yield, to study the reaction kinetics and the effect of mixing as a power per unit volume required for mechanical agitation at conditions near the optimum. Experimental work. Material used, sunflower, local sunflower, methanol, 99.8 purity, calcium oxide, 99.9 purity. The methodology, it is a simple process as a mechanical agitator, a container of 1 liter volume, oil, methanol, catalyst mixed in conditions selected, separation to 2 layers, removing catalyst and methanol to get glycerin and biodiesel. Operating range, agitation speed from 200 to 1000 RPM, reaction time 0.5 hour to 2.5 hour, catalyst content 1 to 5%, at constant temperature 60 degrees C, and alcohol to oil ratio 9 or 200 excess methanol. Reactor as 1 liter, diameter, length, impeller was used, high shear radial flow. A digital adjusted speed mixer was used. This, the equipment setup, not shown. Procedure. Calcium oxide was calcined at 700 degrees C for 2 hours at atmospheric pressure to obtain catalytic active form. The 2 layers from the process, centrifuge separation for catalyst, and the drying in oven at 150 degrees C for 3 hours to remove methanol. Stoichiometric equation is used for calculation by weighing the produced glycerol product. Design experiments. Design expert software 6.606 and response surface methodology center composite design was used. 6 replications of center points to determine the experimental error or poor error. Table 2 shows the coded and actual variables of the 3 process, the variables from -2 to 2. The center point, 600 RPM, 3% catalyst content, and time 1 hour, 1.5 hour. Table 3 shows the experiments design. 20 experiments were planned to do the plane. The result, general analysis of result. Second, polynomial response analysis done by the software and modified to cancel the insignificant terms N square, T square, the interactions N, T, N, C catalyst, and T, C catalyst were cancelled because they were significantly insignificant. Gives this equation with a standard deviation about 3 and R squared 0.948. The figure shows the predictive to actual values, which shows good fit. The effect of parameters at center values of others shows in one figure. It shows identically same effect of the time and speed of mixer. Reduction in yield begin from 2%. So we fixed the concentration of catalyst content to about 2. This figure shows the effect of catalyst concentration. After 2, there is a reduction, trend of reduction of the yield at different time and different RPM. This figure shows the effect of RPM linearly. The effect of reaction time, as shown in the previous figure, also linearly. Process of optimization. The practical optimization, optimum yield is about 96%. 96% at conditions of 800 RPM, 2% catalyst, and 2-hour reaction time in 3D and contour figures. Reaction kinetics. It's assumed a reversible process depending on concentration to power of triglyceride and methanol. For excess methanol, rate of reaction depends on K apparent and triglyceride concentration to power alpha. This figure shows that one first order reaction is fit and show different rate of reaction at different RPM. The RPM converted presented by power per unit volume by converting speed to power by this simple equation for turbulent flow. This figure gives the yield versus power per unit volume, which is more representative than speed. Some figures were not found. Conclusions. The yield of biodiesel increased linearly with increasing both impeller speed and reaction time in the range studied. The effect of the two variables were almost identical. Negative effect of catalyst amount about 2% on the biodiesel was found. The practical optimum yield of the biodiesel was about 96 at operating conditions of 800 RPM, catalyst 2%, and reaction time 2 hours. First order reaction with respect to the concentration of triglyceride was found at conditions near the optimum. The reaction rate constant were 1.3, 1.7, 2.2 for different impeller speed, 600, 800, and 1000 RPM respectively, corresponding to power per unit volume which is more representative than the speed, 0.9 power per kilowatt per meter cubic, 2.2 and 4.3. The power per unit volume required is more representative than RPM in a study. The reaction time decreased to about 1.5 hour at power per unit volume above 4 kilowatt meter. Thank you.
Thank you, Doctor. Thank you, Dr. Zaid. Now we have time for a couple of questions. Questions? Mhandis Muhammad?
نعم.
بالإضافة إنه في أحد إنه 1 to 5% by weight. It depend مكتوب يعني هي تعتمد على وزن الزيت. شو دخل وزن الزيت في العملية percent؟ بس هاي سؤال.
Thank you. Direct utilization of the oil is a problematic because of the high density, viscosity of the oil, high flash point, high molecular weight, unsaturated material causes يعني راح انا شوي يعني تعذروني اتكلم شوي عربي احسن. تسبب حقيقه مشاكل بالجهاز نفسه بالاجهزه الديزل تتاثر اكثر مما لو كان باي ديزل فعلي. راح يكون التاثير مالته في الانجن يعني تستعمل بدون اي موديفيكيشن. يعني لذلك هو الاويل استعماله مباشر حقيقه مشاكل به كثيره. يعني استعماله ويسبب حتى يعني يسبب كربون ديبوزيشن اكثر بنسبه كبيره وهكذا. ويستعمل هاي الطريقه تستعمل لكل انواع التريغليسرايد، كل انواع الشحوم، كل انواع الدهون. وهي عاده تستخدم يعني فور ريوزد عاده. لكن ايضا احنا يعني دخلنا احنا فقط انه الكاتاليست او الميكسينج، تاثير الميكسينج والبرزنتيشن مالته للباحثين اللي كان يعني نتائجهم متناقضه نوعا ما. احنا ليه المتناقضه صار عندنا مجال للبحث حقيقه. يعني وعدم وجود يعني تاثير الميكسينج بصوره واضحه بالليترشر، وهذا اللي كان السبب.
My question about the catalyst, the carbon, the calcium oxide is coming in, I think, in powder form.
نعم.
But is how much is the cost of this catalyst? Is cheap, and the production process, I think, is simple or difficult?
طبعا الكالسيوم اوكسايد هو من المواد الرخيصة جدا. cheapest than hydroxide, sodium hydroxide, can be reused. Washing the water required for removing caustic soda in product may be cancelled. Many advantages on using heterogeneous CaO catalyst.
Thank you, Professor Zaid. Thank you very much.
Now we will move to our next presentation, which is about computational fluid dynamics in design of multi-phase reactors, novel areas and future trends. This presentation will be dually made. One is remotely using Skype and together with Professor Wei-Yin Chen and Baharat Sajjadi. So I will briefly introduce Professor Chen. He works at the University of Mississippi, Department of Chemical Engineering. He's a professor in chemical engineering and he has 43 years of experience in coal and biomass conversion, and he has been the PI and co-PI of a number of industrial funded projects with a total funding of over 10 million. So Professor Chen, the floor is yours.
I'm William Chen from University of Mississippi, and my colleague, Professor Sajjadi, is going to make the presentation from her office, from her home actually. It's 5 a.m. in her time zone. So I will tend the podium to Dr. Sajjadi.
Thank you so much, Prof. Good afternoon, everyone. My name is Galvan Express. I'm research assistant professor at the University of Mississippi in the United States. As Prof mentioned, time here is 5 a.m., but I'm so glad that I'm able to present my work through internet. I do apologize that I could not attend in this conference. Let's start. The focus of this presentation is on the role of computational fluid dynamics in design of multi-phase reactors, novel areas and future trends. So let's start with the trend line of this presentation. In this presentation, we are going to analyze 5 different case studies, including air reactors, membrane reactors, anaerobic digester, a stirrer vessel, and semi-reactor. All of them are among the most important multi-phase reactors. First of all, what is CFD simulation? Computational fluid dynamics, which stands for CFD simulation, is a multidisciplinary branch of fluid mechanics. In this science, we combine mathematics, fluid mechanics, and computer science to solve a set of equations and finally analyze a system including fluid dynamics. In fact, CFD simulation is able to analyze almost every type of system, including single-phase, multi-phase systems including reaction or non-reacting flows, system including particles, or even CFD simulation is able to analyze structure, shape optimization, and so on. But why we use CFD simulation? What's the advantages of CFD simulation? By using CFD, we can save great time and cost of designing new reactors. And also, by using CFD simulation, we can analyze almost unlimited conditions, which we cannot do the experiment easily, and we can reach to unlimited details of the result. The level of details is practically unlimited. In this slide, I put a very simple strategy of CFD simulation. designing the geometry. This example is a three-dimensional simulation, very simple. In the next step, we should design our system and split it into different cells. Our equations should be solved in each corner of these cells. And in the next step, we should select type of our system, whether it's laminar, it's turbulent, it includes Newtonian fluid, non-Newtonian fluid, viscous, and so on. After selecting the type of equations in our system, we should define almost every single boundary that plays a role in our system. You can see the second line. For example, here we have a single and simple input, output, and a wall. In next step, we should select that whether we want to solve our system of equations in transient flow or in a steady-state condition. In fact, we want to open the equations. We want to discretize the equations in space and time. In terms of time, the equations should send their results to the next time step. And in terms of space, the equation should send their result to the next neighbor step. And finally, we can find our results. Our first case study, early fire reactors. Early fire reactors are in fact a modified version of bubble columns. We are all familiar with such system. Almost about 25% of all chemical reactions happen between gas and liquid phases. We use this type of systems in industry very much because they have low shear rate, high mixing performance, suitable heat and mass transfer. For example, in the right-hand side, you can see very simple early fire reactors that are being used for production of microalgae. In fact, in systems that we have live microorganisms, it would be better to use such systems which have low shear rate. We have three different types of early fire reactors. Two of them are internal loop and one of them is external loop. Internal loop can be divided by a split surface or an internal tube. In our system, we use an air-lift reactor with a split surface. You can see that on the left side we have riser, on the right side we have downcomer. What was the objective of this study? In this study, we wanted to increase the mass transfer between gas and liquid in an air-lift fire reactor without increasing the shear rate. So we decided to increase the turbulency in this system by installing some handmade packing. At first, we analyzed this system by using CFD simulation. In all systems, we should consider continuity equation, momentum equation, turbulence, and the type of parameter that we want to analyze. We should select the related equation. For example, here the objective is to analyze the mass transfer, so we use 5 different mass transfer equations. In CFD, we would always better to analyze different type of equations to reach the best result. By doing so, we could analyze velocity, fluid flow pattern, gas hold-up, Reynolds number, and volumetric mass transfer coefficient. Look at our first set of results. On the left-hand side, you can see the mass transfer distribution in the system. In air-lift without any packing, in air-lift with 1 column of packing, and in an air-lift with 2 columns of packing. I discussed the mass transfer in parallel with the effect of packing column on velocity in the system. In the photo on the bottom right side, you can see the mass transfer. At first, the most important thing is that we reach the highest mass imprison very small amount of gas. In fact, the volume fraction of gas that was imprisoned below the packing. But with increasing the packing into two columns, not only we increase the velocity in the system, turbulency in the system, but we also increase the residence time of gas bubbles by imprisoning them at the below of the packing column. As you can see in the contours, the volume fractions of packing are observable. And about the different models that we selected, you could see easily that in one of them we have a large overestimation, in the other we have a large underestimation. But in three of them we reached to almost good results. The results of these papers were published in Communication in Heat and Mass Transfer. The next case study is membrane system. In recent years, membrane received great attention because they can behave the role of both separator and reactor. For example, in biodiesel production, in bioethanol production, in wastewater treatment, in all of them we can see the application of membrane reactors, because in this system we can selectively remove the products from the reaction mixture, we can control the addition of reactants, and we can intensify the contact between reactant and catalyst. In our case, we wanted to use membrane system to increase the yield of biodiesel production through transesterification. So, at first I would like to discuss about the transesterification reaction. Transesterification is the most common reaction used for biodiesel production. In this reaction, in fact, it's three stepwise and reversible reaction, in which at first step, triglyceride is converted to diglyceride, then diglyceride is converted to mono, and then to glycerol. At the end of this reaction, we have 3 molecules of biodiesel and 1 molecule of glycerol. In our system, we designed a system including a membrane, a packed bed membrane that could produce biodiesel and also purify it. The material of our membrane is titanium oxide on aluminum oxide. In this system, we pack the membrane with a type of catalyst that we designed it, we made it ourselves. It was potassium hydroxide supported on activated carbon. For simulation of this system, we just simulated the section of membrane and its catalytic bed. In order to reduce the computational cost, we just simulated half of the system. It's very common in safety simulations to just simulate only half of the system whenever the system is symmetric. The first set of results can be seen here. The first thing that you can see is the system is fully laminar. And the second thing is that the maximum of velocity can be observed in the center of the catalytic bed. And the third thing is that by almost 80 seconds, the liquid can reach to the end of this system. In the next step, we simulated the reaction into 2 different temperatures, 50 and 60. You can see the rate of biodiesel production and also glycerol, the reduction of methanol, and the 2 byproducts, monoglyceride and diglyceride. By adding these reactions to the system, we not only could analyze the concentration of all components in every single second and every single point, but also we could optimize the system. The first counter shows the triglyceride A. The second one shows the concentration of methanol that we use extra to support the reaction and in fact to speed up the process. The third photo shows the diglyceride concentration followed by monoglyceride, glycerol, and fatty acid. If you divide the membrane system in your mind into two parts, at the first half of the system, we can see the concentration of diglyceride is higher, and in the second half, the concentration of monoglyceride. If you look at the glycerol and fatty acid methyl ester, you can see that. Any problem, Prof? Okay. You can see that the concentration of biodiesel is at the maximum level at the second half of the system. But we just cut the system at the maximum concentration of biodiesel. So in fact, by using CFD simulation, we could analyze and optimize the length of the system. Again, the result of this work were published in Field Process Technology and also in Journal of Industrial Engineering Chemistry. The third case study. Currently, over 50% of world's water supplies are severely polluted with untreated domestic, industrial, and agricultural wastewater. It has been estimated that over the next 50 years, almost 50% of world's population will suffer from shortage of water, pure water. What's the solution? The solution is to purify the water that we are consuming. One of the best strategies is by using anaerobic digester. Anaerobic digestion is a biological and economical process. In this process, we convert the organic waste into energy. The byproducts will be purified water and also biofertilizer. In the system that we simulated, we wanted to mimic the behavior of highly viscous liquid. So we used a system with submerged jets for input, and also you can see the output. Again, half of the system was simulated in order to reduce the computational cost. The experimental section of this project was performed and accomplished in RMIT University of Australia, and our group has done the safety simulation section. You can see that first of all about the viscosity of this system. In this system, you know that if we use 15% of xanthan, we can mimic the behavior of highly viscous liquid with almost 2% of solid particles. In this system, we use 0.3% and 0.4% of xanthan in order to increase the viscosity of the liquid to mimic the behavior of highly viscous non-Newtonian sludge. If you compare the practical and experimental photos with results of safety simulation, you can see that we could exactly predict the behavior of active zones in the system. Objective was to reduce the volume of non-active section. Yes, bro?
We have 2 minutes,
okay.
please.
Okay. In this system, we could, at first we analyze the velocity, and then in order to reduce the concentration, the volume fraction of dead zones, we analyze the viscosity. What we observe? We observe that whenever we have 50% of our system full with active material, almost 80% of our output is active material. In fact, we are wasting our material. So the location of input and output section were not suitable in our system. You can see the validation results. The next system. I think I should jump one of the system, but I can complete the fourth case study. In this system, the objective was to define a new role for baffles. You are familiar with the baffles. In baffles, we use the baffles in external vessel to break the vortex and increase the turbulence. But in our system, we defined a new role for our baffle. We defined a synergistic interaction between baffle and impler to increase the suspension of our particle velocity by using lower impler rotating rate. You can see the contours and vectors of velocity in the system. In our system, we guided the liquid from the center toward the implers. By analyzing the system practically, you can see in almost 22 seconds, after almost 22 seconds, we suspend whole particles uniformly in the system. But in a normal system with a simple baffle, we could reach to almost 50% of suspension. Again, after analyzing the impler rotating rate, you can see that by almost 100 rounds per minute, the suspension is completely 100% in the system, including orienting baffles. But in a normal system, we reached to almost 50% of our suspension. Thank you so much. I just skipped the last case study, which was solar reactor. But if anybody is interested to have this file, I can share the file with you. And thank you so much. This work was supported with NSF from United States government. I put my email. If you have any question, you can send it to my email. I will be glad to answer to your all questions. Thank you so much.
Thank you very much, Dr. Baharag Sajjadi, for your excellent presentation.
Thank you too.
It's nice to use this technology and to talk to others despite this long distance between each other. We are out of time, so I can allow one question. If there is one burning question, we can accommodate that. Dr. Omar, Professor. There is mic here.
No, I can come here.
Please.
Good morning.
Good morning.
I would like to ask about the effect of mixing on the equation. How does that affect your physical properties of the material? And how is that reflected on the solution of your equations?
How it reflects on what?
Solution of your equations, since your physical properties will be affected by degree of mixing.
Yes,
Thank you.
You mean about the CFD simulation, right? Or any of the case studies?
Beg your pardon?
You are talking about any of the case studies or just about the CFD simulation overall?
No, I would definitely would like to know your views on, you have simulated, you have results from computer. Now,
yes.
If somehow the mixing is not proper, or somehow non-ideal systems exist, how does that, in your views, in your opinion, does reflect on your solution of equation?
Okay, in fact, it does not reflect on equation, it reflects on final results. But definitely the mixing intensity does not destroy all of the results, but it increases the level of error in our system, the level of mistake. It results in overestimation or underestimation. So, whenever you want to do a CFD simulation, at first highly turbulent. But if the system is non-turbulent and laminar, we just should deactivate this equation in our system. If you select the turbulency K-epsilon model, then we have to select the correct parameters. So by analyzing the system experimentally, we can reach to those parameters. In CFD simulation projects, most of the time we should simulate the process several times to increase the accuracy of the system. In each level, we can increase the accuracy and we can reach to better parameters.
Thank
so,
you.
Finally, okay, thank you so much.
Thank you very much. Thank you. Now I will move quickly to our next presentation. We will move now to our next presentation, which is about catalytic phenol oxidation with phase change in periodically operated trickle bed reactor with Dr. Farah Al-Sudani. Let me give you just a brief introduction about Dr. Farah. She works in the University of Technology of Baghdad in the Chemical Engineering Department. She has her PhD in 2008 from the University of Technology Department of Chemical Engineering Baghdad, and her master thesis in 2001 from University of Technology, and the same thing is from her bachelor degree in 1998. So, are you? Okay, please come in. 3 years. Okay, the floor is yours.
Assalamu alaikum. Catalytic phenol oxidation with phase change in periodically operated trickle bed reactor. Catalytic phenol oxidation with phase change in periodically operated trickle bed reactor. The most common pollutant are the phenol and the phenolic compound which presents in the wastewater from oil refineries, coal conversion process and pharmaceutical industries process. And these pollutants need to treat it before it's released. These weights of phenol and in the range of 500 and 5000 per end are too toxic and concentrated for biological treatment. So that within this concentrations and toxicity, that the catalytic wet oxidation has been shown to be the stable extraction technique, and advantage lay to the low operating costs and minimal requirement for the pressure and temperature. And the most, the catalytic wet oxidation process fall into the category for the catalytic three-phase reactor, fixed bed reactor, and the best reactor for the best treatments, it's lay for the trickle bed reactor. Other reactors use a slurry fluidized bed reactor, but more the researchers used the trickle bed reactor. The challenge design lays for challenge overall outcome process relay complex manner interface intraparticle diffusion chemical kinetic and thermodynamic flow regime and hydrodynamic. Trickle bed reactor operated in trickling flow regime, liquid evaporation may occur, which makes the possible and composed of dry regime in catalytic pellets. And the reaction takes place on dry catalyst surface, and various possible situations for the catalytic pellet can result for the evaporation of liquid following over the external catalyst surface. خلال دراستنا راح نستغل هذه الفقرة اللي تحدث اللي هي الايفابوريشنز اللي بتحدث بالتريكلينج ريجنز، فاستغلينا هذه النقطة partial wetting. أيضا التشالنج الآخر اللي هي أنه most studies working a trickle bed reactor in steady state operation. most challenge الأخرى هي أنه عندنا الريزيستنس. نريد احنا نحاول انه احنا دمج. كيف احنا نحاول ان احنا نقللها؟ نحاول احنا نقللها يعني بنيو اوبريشن. نيو اوبريشن هي اندر سايكلينج اوبريشن اللي هي periodic او ان هي unsteady state operation which one or more operating parameter. أفضل الأنواع اللي هي كانت عندنا اللي هي liquid flow modulation، بعضها يستخدم اللي هي concentration modulation. Liquid flow modulation is forced or reacting to operate continuously in transient modes such as the liquid flow modulation. It's required to enhance the mass transfer characteristics of the emitting reactant in multi-phase reactor, so the periodic operation technique seems to be a favorable tool to enhance the performance of trickle bed by cycling liquid evaporation operation. on-off cycling اللي هي استخدمناها. بعض الأنواع اللي يستخدمين هي base peak cycling. Present work aimed to investigate catalytic weight air oxidation over porous catalyst particles 0.5 platinum gamma alumina in non-isothermal operation to generate the phase change for steady state and periodic operation. The influence of the key parameter on the performance on non-isothermal operation such as periodic operation اللي هي parametric periodic اللي هي cycle period and split. Furthermore, space-time, bed temperature, superficial gas velocities for steady state operation, kinetic analysis are also studied. This table shows the catalytic reactor material characteristics used in the experimental work and the range of operating condition used. Before in the experiments, in all experiments were initiated after the reactor, we must before the cycling or the periodic operation, we must initiated the steady state experiments in order to compare the results. Also, to compare the results. These equations for the convergence and the enhancement conversion and the cycle separates. بس اكو from this figure, it can be how it can be the estimated the it can be the apparent activation, it can be the apparent kinetic rate for the steady state, and the for the steady state and periodic operation. From the table, it can be for the steady state, it is the lower than the periodic operation. For the periodic operation, the cycle split used 2 minutes, 9 minutes, and 60 minutes. A cycle split 0.25, 0.62, 0.45, and 65. The optimum cycle period is 9, as it can from the apparent kinetic period. من خلال النتائج لاحظنا انه الابرنت كاينتيك ريت انه يعطينا انه افضل النتائج انه من خلال تحليلها انه يعطينا افضل القيم اللي هو من خلال when we compared with the other results انه المينرال الفينول مينراليزيشن ده ينطينا اياها افضل شيء اللي هي ات سايكل سبلتس اللي هي سايكل بيريود اللي هي 9 minutes. عندنا الاكتيفيشن انرجي ايضا فور ستيدي ستيت هي تعطينا اياها افضل فور بيريودك اوبريشن تعطينا اياها افضل مما لو هي عندي ستيدي ستيت، لكن فور 2 سايكل بيريود 2 minutes هي لا اسوء مما كنا نتوقعها. تنطيني اياها فينول مينراليزيشن فور كاربوكسيليك مينراليزيشن. effect of operating condition on performance of trickle bed reactor. نلاحظ من خلال هذه الفيجرز for steady state it can be seen that the phenol conversion and the enhancement أيضاً أنه عندنا كل ما كانت عندي البيد temperature أعلى and the space time أعلى كل ما كان أفضل. ده يحسن لي الفيز تشينج عندي، لكن الفيز تشينج بالستيدي ستيت ده ينطيني الماكسيموم 7 ديجري، ده ينطيني الماكسيموم 7 ديجري. لكن لو قارنت مع البيريودك اوبريشن لا، بحيث حصلت على 100% conversion and enhancement conversion، بحيث حصلت enhancement conversion وصلت للواحد. هنا حصلت على الفيز تشينج، بحيث حصلت على الماكسيمم الفيز تشينج وحصلت على الماكسيمم الزياده بدرجه الحراره رايز تمبريتشر حصلت على 20 ديجري. التريكل بيد رياكتور من خلال النتائج هنا انا يعني دا يشتغل اندر غاز ليميتد رياكشن، وهذا اللي هو اللي قدرت انه ساعدني انه بدي احصل على الفيز تشينج اللي دا اريده. خلال هذه ايضا جينا نريد نشوف نقارن بين الستيدي ستيت والانستيدي ستيت من خلال هذه البيريودك اوبريشن. هذه الفيز تشينج اللي اريد اشوفه انه انا فعلا خلال 9 minutes قارنت بين السايكل سبليت بين ال 0.25 0.45 انه خلال ال 0.25 حصلت على 20 ديجري زياده بدرجه الحراره، لكن عندي خلال ال 4.44 حصلت على 16 ديجري. Conclusion: the present study aimed to investigate the effect of periodic operation, the oxidized of trickle bed reactor using on-off mode liquid flow modulation showed that the performance of catalytic or oxidation has been significantly enhanced. نسبة الزيادة under periodic operation maximum from 14 إلى 84% to maximum value at cycle split and 9 minute cycle period. لكن دا أحصل على drops من 30 إلى 54% lower to steady state value at higher cycle period under identical operating condition. السبب لأنه دا أحصل على هنا المينرايزيشن دا ينطيني الكربوكسيليك، ما دا ينطيني اللي هي اللور موليكولر ويت، إنه بدا ينطيني هالمرة مواد سمية أكثر. With the steady state, it was shown that the temperature effect has an exothermic reaction. Cycle coating of catalyst surface are strongly influenced by modulation parameters such as cycle period and split. Higher temperature amplitude attained is 20 degree when initiate temperature, bed temperature 165 degree. At space time 0.8 hour. Optimum cycle period is 9 minutes. Cycle split 0.25. For periods operation, activation energy varied with the cycle period and cycle split due to the change reaction mechanism from kinetic reaction to gas phase reaction. periodic operation اللي حصلناها الفيس تشينج ايضا اللي ساعدني انه دا يخلي لي انه دا يبدل لي الميكانيزم بالستيدي ستيت عندي ميكانيزم ثابته اللي هي كاينتيك كنترول. اما بالبريودك لا، حصلت انه عندي الميكانيزم دا تتبدل كاينتيك، يصير عندي variation طول الوقت بالميكانيزم from kinetic to gas phase mechanism kinetic to gas phase mechanism. هذا دا يخلي لي انه الكونفرجن قدرت انا احصلها لل 100% وايضا المينراليزيشن قدرت احصلها CO2 and H2O. Thank you.
A sheet of graphene with 3 different types of upstream functional group on it. This is the key of our discovery. And a few years ago, we initiated a sustainable energy and environment group at the University of Mississippi. It's a new challenge for us. So we start by educating ourselves, by offering new courses, editing a set of handbooks, doing collaborative research, and also develop experimental modules for education purposes. Some of our participants already graduated with distinction. And the handbook has been published for 2 editions. And to me, we also get an NSF grant, $6 million grant, which involves 4 universities. And we are hoping we can expand our activity in the future to international collaborations. Today's talk, I'm going to talk about how the idea comes from and how we demonstrated our hypothesis. And it's really exciting to share with you in a single stage of treatment of biochar in water with CO2, it can gain remarkable benefits. And then I will discuss 4 technologies we are trying to develop. And the project originally started from a very simple idea. We would like to see if CO2 can be fixed on carbon, any type of carbon. The project started mainly with a desire to know much about how CO2 can react with different type of carbon, so we can capture CO2, also we can utilize the resultant carbon. This is the original program started. And we also put our focus on photochemical reaction and ultrasonic energy for simple reasons we will discuss shortly. For photochemical route, of course, solar energy is renewable. That's the primary aspect. In order to fix CO2 on carbon and also bring the CO2's heating value to higher energy level, energy must come from somewhere. Of course, the solar energy irradiation will be a logical choice. And we also discovered there is such photochemical reaction going on, which I will discuss shortly. And if we can fix CO2 on carbon and reburn it at a high energy value, then we succeeded in a cradle-to-cradle carbon cycle. So that was the primary objective. And we also, once the photochemical reaction started, we also started injecting the ultrasound. Ultrasound can leach mineral. Mineral can be leached out into the solution, that's known. And also, ultrasound can split water. And the biochar tend to like hydrogen rather than OH radical. So this is another reason. And finally, in the last 10 years, ultrasound has been used to split the graphitic oxygen, graphitic structure. And that is the main skeleton in the biochar. So we would like to know if ultrasound can break up the biochar structure so that the reaction can take place more vigorously. That's the primary aspect. And this slide lists all the reasons we perceive, which I will go through this one at a time. When the project started, we looked for the CO fixation on carbon. And this is about the only reaction we can find from the organic chemistry textbook. Basically, CO2 can be fixed on the carbon next to the phenol. And then my colleague, he is an organic chemist. He said, well, this is not a product you would like to have because this compound has 2 more oxygen in there. So the heating value is not going to be attractive. So, but I argued this has not been considered a main route for CO2 capture. And also the desorption energy is an important criteria for CO2 capture, is compatible to the current amine adsorption process. Then we discovered this paper. This is a very important paper to us. This is how our work started. Basically, Chalcopyrite discovered that CO2 can be fixed on the ring H carbon, and the resultant product is also hydrogenated. So this product has a high heating value than the reactor, and this requires the use of photochemical irradiation. To achieve this reaction, Chalcopyrite used propanol as a hydrogen donor. He used a amine as an electron donor to induce the photochemical reaction. So this really inspired our subsequent work. So we are wondering, if we can use light to induce such reaction on biochar. And from the photo, this is for ultrasound. If graphene is oxidized, there are oxygen diffused between the layers, and ultrasound can be used to break it up. This is a known procedure for people working on the graphene oxide. So we are wondering if we can break down the biochar structure into pieces. And another reason is the solvent we are using include water and CO2. Both are polar species. They are known to swell the carbon. Once the carbon is swelled, its reactivity enhanced. So this is another reason we designed a set of very simple experiments. And this is a cartoon which depicts the biochar structure. It has clusters of graphene oxide, graphitic oxide, etc. And in between the clusters, it has titanium dioxide, which is an electron donor. It's a photocatalyst. And water is known to be a hydrogen donor. So we are wondering if we can design a system which involves biochar, water, and CO2 to induce some photochemical reaction. So this is what we did. We use sorghum for biochar production. We heat up to 550 degrees C and then treated 3 to 6 grams of biochar in a double neck flask. And then put this flask in the photo irradiation or a laboratory ultrasound cleaner. And here is the summary of our result. Carbon from CO2 is fixed on the biochar. Hydrogen from water is also fixed on the biochar. And oxygen from these two compounds do not like biochar, so they tend to be turned away. Interesting. We are in the process of finding out the reaction mechanism. Internal surface area can increase 14-fold. So we are wondering if this internal surface area increase can be used as a carbon activation procedure. And this is the foundation of our current project. And also mineral are leached out of the biochar solid. As a result, the heating value of the biochar increased by 50%. So our postulation that such treatment can be used to increase the heating value of biochar, capture CO2, and reburn at a higher heating value. This is the idea, crater to crater idea we have demonstrated. So this is the University of Mississippi's work. We have a consortium involving 4 universities. University of Mississippi has 2 main groups, energy and environment. We modified the biochar by using ultrasound, photochemical irradiation, and also chemical irradiation chemical modification of the surface. We found combination is a very powerful technique. About 2 hours ago, we heard Dr. Sajadi present her CFD modeling work, and so this is a way to save the energy consumption during the treatment. And we are developing applications in different areas. CO2 capture is one of them. Water treatment is another subject. We are converting CO2 to useful fuels because we believe the underlying chemistry has a hidden secret to convert CO2 to fuels. So we are working hard on this. We also have some interesting results to share with you today. So the heating value increase of biochar can be used as a gasification pretreatment technology. This is another technology we are not currently funded yet, but we hope we can get another big research grant to do this type of research. We are also hoping to incorporate plasma modification of surface because ultrasound can induce the internal pore size, surface area. Plasma can modify the surface functional groups. And all this technology we are talking about are conducted at the room temperature, essentially at the room temperature. So no energy other than the ultrasound energy, photochemical energy are involved. So the conventional carbon activation involves 700 degrees C. So there is a tremendous energy saving in terms of this kind of treatment. So I will be quick to report what we discovered in these 4 areas. We treated biochar by ultrasound, break it up into single layers, then we modify by activation agent, sequentially activate the different functional group on the graphene oxide sheet, and then use that to capture CO2. And these SEM images are very interesting. You can see closely raw biochar has filled holes. Presumably these are minerals. After ultrasound study, these holes are opened up. And after we treated the ultrasound treated biochar with activation agent, I was talking about in the last slide, we see these holes are refilled and the surface are covered by the activation agent. And also in both steps, the surface area increase, CO2 capture is remarkable. So this is an interesting discovery. Then let me talk about the second technology we are looking at is to increase the heating value of biochar by using ultrasound study. This is the technique I was mentioning. In order to save the energy, we put the ultrasound home directly into the solution and bubble CO2 through the solution. And this type of home can measure the energy going into the solution. It directly report on the ultrasound instrument. So we clearly see the benefit of treatment on the energy gain of the biochar. And notice this scale is much higher than the energy consumption. So I think this is an exciting part, and our ultimate goal is to develop a technology that consider ultrasound or photochemical treatment as a pre-treatment technology prior to gasification. So this is the second technology. And the third technology, this concept started from a colleague and I during had a discussion during the coffee break. He is an organic chemist. I asked him casually if C1 chemistry is involved. CO2 can dissolve in water, then it's converted to formic acid, then formaldehyde, then methanol. So I asked this organic chemist, can formaldehyde react with biochar? He immediately said yes. It can form compound. It can react with a benzene ring, H carbon on the benzene. So if that reaction takes place, it can react with biochar for sure. So we want to demonstrate this. And if this can be demonstrated, we discover some interesting reaction mechanism, how to convert CO2 to valuable fuels. So this is the initial idea. CO2 to formaldehyde, then carbon is fixed on biochar. And here's what we discovered. Let me say just from the three major pieces of conclusion. Indeed, biochar can be converted to, photochemically converted to formaldehyde, but the ultrasound doesn't. Number two, formaldehyde can be fixed on biochar surface, and that is enhanced by light and the ultrasound. But the CO2, the correlation of formaldehyde disappearance to CO2 environment. We use the CO2 environment and the N2 environment in the glove box. We found that CO2 actually cause the formaldehyde disappearance higher. Higher. So it doesn't make, CO2 make CO2 disappearance low. So it doesn't make sense to us. So the only conclusion we can draw is that CO2 and formaldehyde both play double roles in the system. So this is what we discover for now. And let me just make a conclusion about the fourth technology we are developing. That's trace metal removal from wastewater. Again, it shows the biochar, raw biochar has filled holes. Presumably these are mineral. And after ultrasound study, we see the holes open up. Then we use urea to coat the biochar again. Second treatment, use urea to coat it. And we found, again, the surface area increased after the treatment. And both ultrasound and the urea help the nickel removal tremendously. Almost complete removal can be achieved. So, as a conclusion, I think we develop a technology to activate the carbon at a room temperature, which involve much lower energy consumption than the traditional method. And we are developing different technology to use the biochar. Biochar is widely spread, and it's a byproduct in bio-oil production. This concludes my talk. I'll be happy to answer questions.
Now we open the floor for a few questions. Sir? Where is the mic? Mic here. Mic, where is the mic?
Where's the microphone?
It's okay, please, just without mic.
I have to apologize. I have a hearing problem. It's in my family gene. I cannot help. And my hearing aids is in my luggage, which has not arrived yet.
Can you hear me? Can you hear me? Yes, we hear you. Yes. I'm talking about, my question is, first of all, thank you for your presentation. And I'm asking whether the technologies you are presenting is viable to the industry. And if you're talking about carbon, you're talking about graphene. Graphene as a nanomatrix is quite expensive. From my personal experience, 1 gram of graphene is $150. So is it viable for the industry to do CO2 capture, and you're still paying so much money for the graphene to process it? Thank you.
I think this is going to be another interesting research topic. In another set of slides, I do have one include that. If biochar can be used as a source of graphene oxide production, the answer is yes. I think it's possible. And think this way, the biochar structure I show you, this biochar cartoon actually is not very new to the fossil fuel combustion community. Rosalind Franklin, the so-called Dark Lady of DNA, reported such a structure for coal-derived char back in 1951. And the petroleum residue produced from petroleum coke also has a very similar structure, which is reported by T.F. Yan of University of Southern California in 1961, I think. So to answer your question, I think the answer is yes. I think there's a lot of research opportunity there. Not only biochar, petroleum coke. If you are interested in oil shale, I don't know if oil shale production involves residue. The residue should have very similar structure. So if that can be used to produce single sheet of graphene oxide, yeah, this is another challenge I think we can investigate. As far as the technology we are developing, I think they are all in the test tube, a very bench scale study. And that's,
so your graphene should be in the nanoplatelets? Your graphene that you're using, the carbon that you're using should be in the nanoplatelets? And the different, have a specific layers and thickness to be used. Did you investigate this area? Because if it is in the nanostructure, it will be very expensive.
It's, I believe it's slightly larger than the narrow size. There is a very famous book on biochar by Lehman and Joseph, published in 2015, second edition of the book, has a discussion about how these clusters form. Really wonderful work, 2015 by Lehman, Lehmann, and Joseph. There's a chapter talking about how this cluster form. We are curious about how this form too. It starts from very small to very large. It does start from very small, narrow size, then it grows and it become more organized clusters. So we are thinking to modify, to reduce the energy consumption during the biochar production by, before this cluster form, we use a minimum amount of energy to produce single sheet of narrow size. That's another subject we are interested in finding out, and we are using molecular dynamic simulation to do that. We have a colleague with expertise on that.
Okay. Thank you. Thank you very much. Thank you.
Yeah.
Now we will go to our next presenter on our schedule. He's Professor Abdullah Al-Marashli. Abdullah Al-Marashli is working in the mechanical engineering department at Al-King Hussein bin Talal University. He's a full professor since 2004, and he has his bachelor in mechanical engineering from Halab University in 1979. His expertise is in cooling gaseous turbines from the Polytechnic Institute in Leningrad in 1986. So I will not go through all your CV, Doctor. So, and I will leave the floor is yours for about 20 minutes. And the doctor wants to speak in Arabic, but the slides are in English. Okay.
السلام عليكم. أنا بدي أحكي شوي بالعربي فما تأخذوني إذا حكيت in Arabic. سنبدأ الموضوع. بدنا نحكي اليوم عن وضع طاقة الرياح في المملكة الأردنية الهاشمية. لابد من استعراض بعض الأمور الأساسية المتعلقة في توليد الطاقة من طاقة الرياح. سنستعرض بعض المراحل التاريخية اللي مرت فيها، وضع طاقة الرياح اليوم في العالم، استخدامات طاقة الرياح، ومحاسن ومساوئ بعض الأنظمة الريحية المستخدمة، ومن ثم سنتعرف على طبيعة أو واقع الرياح في المملكة والأمكنة التي يمكن استخدامها فيها. الحقيقة طاقة الرياح هي تعتبر من أحد المصادر الرئيسية الثابتة التي ممكن تتوفر على طول اليوم وعلى مدار العام، ويمكن استخدامها في كثير من المجالات، وفي بعض البلدان يعتبر هذا المصدر من المصادر المهمة لتوليد الطاقة. طبعا السبب في اعتماد بعض الدول على الطاقة البديلة ومنها طاقة الرياح هو نمو الطلب على الطاقة في العالم، قرب خلاص أو انتهاء مصادر الطاقة التقليدية، الواقع الاقتصادي أي الكلفة، وتحقيق الأمن الطاقوي للبلد المستخدم فيه، بالإضافة إلى التغيرات المناخية التي تحدث في العالم والمحاسن البيئية الناتجة عن ذلك. نلاحظ في الفترات القادمة ومقارنة بما كان مثلا من 2002 حتى 2025 أن نمو الطلب على الطاقة الكهربائية في العالم يزداد بشكل كبير جدا، أي بحدود 600 بالماء. من خلال الدراسات تبين أنه النمو الحالي في الطلب على الطاقة ينعكس أيضا في الطلب على طاقة الرياح، وحاليا معدلات النمو في الطلب على طاقة الرياح معدلات كبيرة جدا لأسباب مختلفة، أهمها هي رخص مصدر هذه الطاقة ونظافتها بيئيا. فعندما نستخدم 1 ميجا واط ساعي من الوقود نلاحظ أنها توفر، أي كل 1 ميجا واط استخدامها في طاقة الرياح يوفر تقريبا 0.278 طن من الوقود المكافئ، بالإضافة إلى خاصة جدا مهمة في البلدان التي فيها بطالة يمكن أن توفر طاقة الرياح مصادر كبيرة في العمل، أي في الفترة القادمة يمكن أن تخلق فرص عمل تصل إلى 4 مليون. المخطط الحالي عم يبين لي أنه نمو الطلب على طاقة الرياح هي أكثر بكثير من معدل الطلب على كل مصادر الطاقة التقليدية الأخرى، بما فيها المصادر الشمسية والنووية وما شابه ذلك. السبب في ذلك حقيقة ينحصر في سببين رئيسيين. السبب الأول هو كلفة التوليد من طاقة الرياح، كلفة منخفضة جدا مقارنة بأغلب المصادر ما عدا الهيدرو باور، أي الطاقة الهيدروليكية. عم نلاحظ أنه سعرها الحالي يتراوح بين 4 إلى 7 سنت لكل كيلو وات ساعي واحد، بالإضافة إلى سبب آخر وهو السعر التأسيسي أو سعر الكلفة التأسيسي لمحطات طاقة الرياح هي أيضا على الرغم من سعرها المرتفع تقريبا إلا تبقى ضمن المجال الذي ينافس بقية المصادر الأخرى. هذا الشكل عم يعرض لي تقريبا الكلفة التقديرية في أغلب بلدان العالم المستخدمة لطاقة الرياح تتراوح قيمتها تقريبا من 4 سنت ل 12 سنت في الواقع الحالي، تختلف من بلد إلى بلد حسب حجم المنشأة، حسب المكان، كلفة العامل، الأرض ومصادر أخرى. تاريخيا طاقة الرياح بدأت من فترات طويلة جدا، من 5000 سنة تقريبا استخدموها المصريين القدماء، استخدموها السوريين، والآن لها استخدامات واسعة في كثير من البلدان، منها محطات الضخ، منها في الطحن وتوليد الطاقة الكهربائية، وخاصة في المناطق الحضرية أو المناطق النامية. بنشوف الصور تقريبا بتعرض لي شبه تطور تاريخي للأمكنة التي استخدمت فيها طاقة الرياح. حاليا يتم التركيز أو البحث في مصادر طاقة الرياح على جملة من الأمور، أهمها أن السكيل أو المقياس تبع محطات الطاقة الريحية يزداد، الناحية التجارية، قدرتها على المنافسة، وإمكانية ربط هذه المحطات بالشبكات الكهربائية. طبعا المحفزات المؤثرة في هذا البحث هو محفزات اقتصادية، محفزات أمنية طاقوية، بالإضافة إلى مصادر بيئية أخرى. حاليا أغلب المحطات المستخدمة هي محطات ثلاثية الشفرات، الهواء يهب من الأمام، وضع المحاور هو أفقي، ووضع الأبراج هو وضع برج واحد وليست متعدد. الآن وصلت الواقع الحالي في محطات الطاقة الريحية إلى ضمن عنفة واحدة. عم نشوف 2016 شركة ألمانية فيستاس صممت عنفة وصلت استطاعت العنفة الواحدة إلى 8 ميجا وات، وعم نشوف أنه ارتفاعها تقريبا قريب من 200 متر، وفي المستقبل القريب راح نشوف استطاعات ممكن توصل إلى 20 ميجا وات ضمن عنفة واحدة، إلا أن عم نشوف أنه أبعادها كبيرة جدا. يعني وزن الشفرة الواحدة أو البليد الواحد ممكن يوصل إلى 35 طن واحد، عرض الجناح ممكن يوصل إلى 8 متر. طبعا لها قدرة على توليد كهرباء مثل ما شايفين خلال 24 ساعة 216 ميجا وات ساعي، وهذا الرقم مسجل فعليا. طبعا أيضا استعراض تاريخي في أحد البلدان المتطورة في مجال صناعة العنفات التوربينية الريحية هي الولايات المتحدة. تاريخيا وصلت الآن الاستطاعة أيضا قريبة من 4 ميجا وات في الواقع الحالي، وعم نشوف تطور الأبراج كيف استخدمت. بعض البلدان متطورة أو تتميز عن بعضها الآخر في معدل التوليد الممكن توليده من المحطة، بالإضافة إلى قطر الروتور، وهي أغلب البلدان طبعا البلدان المتقدمة في هذا المجال خلال فترة تاريخية تقريبا 10 سنوات. أغلب الاتجاه الحالي في تصنيع طاقة الرياح هي على المحطات الموجودة على الأرض وليست على شاطئ البحار. عم نشوف جزء بسيط على الشواطئ البحرية، إنما أغلبها عم بيكون مركب في المناطق يعني الممكن الأرضية أو على الأرض وليست في شاطئ البحر. عم نشوف الجيجا وات قديش وصلت الاستطاعة في العالم في 2015 إلى تقريبا 60 جيجا واط ساعي في العالم. أيضا مقدار الانفستمنت أو الاستثمار في هذا المجال ارتفعت خلال فترة زمنية مقدارها 10 سنوات من 20 إلى 100، أي 5 أضعاف ما كان من بال 2004، وهي مبالغ كبيرة جدا. طبعا لو استعرضنا قدرة هذه المحطات على المشاركة في توليد الطاقة في كل بلد من بلدان العالم، أغلبها هذه المتطورة. مثلا في الأردن ممكن نأخذ أرقام لا زالت صغيرة جدا المشاركة، إنما مقارنة في بلدان أخرى كالصين 33% من الطاقة المولدة في الصين على سبيل المثال تؤخذ من الطاقة الريحية، وهي متدرجة حسب البلدان. مثل ما شايف جدولنا البلدان العربية أغلبها مقصرة في هذا المجال. طبعا الأبحاث الحديثة والاتجاهات الحديثة في تطوير الطاقة الريحية يتركز حقيقة في 3 أمور أو اتجاهات رئيسية. أولاها يتركز في التركيز على تصميم العنفة نفسها، التوربين. المقاس عم يكبر، ممكن يوصل إلى 20 ميجا واط، من خلال التقليل من الضياعات الميكانيكية على الجناح وتقليل الإجهادات الميكانيكية، كون الجناح كبير جدا ممكن يوصل قطر إلى أكثر من 200 متر. الناحية الثانية هو تأمين الإدارة المباشرة بدون علبة سرعة، أي يتم تحويل الحركة الدورانية مباشرة إلى طاقة كهربائية دون المرور في الجير بوكس أو علبة السرعة. الناحية الثالثة وهي التحكم الإلكتروني عن بعد باستخدام معطيات الأرصاد الجوية المتوفرة، بحيث دائما أو مباشرة تؤمن أو تدور العنفة بالطاقة اللازمة حسب اتجاه الرياح وحسب سرعة الرياح في المنطقة، باستخدام تقنيتين، هي التقنية الأولى الليدار والتقنية السولار. إحدى الصناعات الحديثة الآن اللي عرضوها في باريس في مؤتمر المناخ العالمي اللي صار من تقريبا من عدة أشهر، نتيجة الحديث اللي صار عن التأثير البيئي لمحطات طاقة ريحية، بدأوا ينتجوا نوع من الأشجار اللي الأشجار مولدة للطاقة. ميزة مثلا هذه الشجرة الريحية اللي ممكن تعطيني طاقة ممكن توصل ل5 ميجا واط. الأوراق تاعها مصنوعة من البلاستيك الرقيق وممكن تدور عند أي سرعة رياح. طبعا لا زال كلفتها شوي مرتفعة، لكن في المستقبل القريب ممكن نشوف هذه الأشجار مزروعة في أغلب المدن، منظرها مقبول جدا، تؤمن استطاعة على مدار الوقت، خاصة إذا توفر لها فيها التخزين المناسب، وهي دون أي ضجيج، بالإضافة لأنها تدور عند سرعات منخفضة ريحية لا تؤمنها بقية المحطات. هذا نموذج عن يعني تفصيلة داخلية لهذه التوربين. منظرها البيئي مقبول، ارتفاعها تقريبا بحدود 9 أمتار، قطرها بحدود 7 أمتار، فيها 54 عنفة، وهي من التقنيات الحديثة الآن المستخدمة في توليد الطاقة، خاصة في المناطق السكنية أو في المناطق البيئية. من أهم الاستخدامات الحقيقة في العنفات الريحية أو التوربينات الريحية استخدامها في التوليد الكهرباء في المزارع الصغيرة، ممكن استخدامها بشكل وسطي في الصناعة، ممكن استخدامها في التوليد في الشبكات العامة للكهرباء، بالإضافة إلى استخدامها في المناطق البعيدة حيث لا يمكن وصل الشبكات، وخاصة في الإدارة الميكانيكية أو في محطات الضخ. مثالين بيعطوني أمكن تطبيق طاقة الرياح في محطات الضخ أو محطات الضخ التي تنقل الغاز وتنقل الوقود إلى أماكن أخرى. لن أتوقف كثير عن المحاسن والمساوئ لكل نوع من هذه الأنواع نظرا لضيق الوقت. طبعا هي لا تشغل مساحات نسبيا كثير كبيرة، خاصة في مناطق كالمملكة المساحات متوفرة. السعر الموجود مقارنة بالأسعار الحالية للطاقة هي سعر رخيصة، وهي ممكن تكون اقتصادية في المناطق الحضرية. المساحة اللي بتشغلها مساحة مش كتير كبيرة مقارنة ببقية المحطات. طبعا من محاسنها بيقولوا الكلفة التقديرية كتير كبيرة لكن أسعارها عم تنخفض. الضجيج اللي بتولده نسبيا هلا بعد شوي ممكن نشوف انه الضجيج مش كتير كبير، بالإضافة إلى المظاهر العينية ممكن يكون المنظر مش كويس، ورد على ذلك شفنا الشجرة اللي قبل بشوية ممكن أبدا يكون منظرها جدا مقبول. حاليا الكلفة التقديرية لكل كيلو واط تركيبي يستمر في الانخفاض، وممكن في المستقبل القريب ينافس بقية المحطات التقليدية. لطريقة تحويل طاقة الرياح إلى طاقة دورانية أو طاقة ميكانيكية نماذج كتير كبيرة، منها ذات المحاور الأفقية ومنها ذات المحاور الشاقولية، منها تدور بسرعة بطيئة ومنها ما تدور بسرعة أعلى. إنما مثل ما شفنا قبل شوي أغلبها توقف عند النموذج ثلاثية الشفرات لعوامل تتعلق في التشغيل اللي هي تريبل بليد. النموذج الأساسي للمحطات أو للعنف الريحية الأفقية هو تقريبا بهذا الشكل، فيها نظامين كتير مهمين، هو نظام الياو سيستم مشان التدوير، ونظام درايفر مشان أو مهمته القيادي، بالإضافة للبيت سيستم مهمته التحكم وتدوير الشفرات بالاتجاه المناسب. هذه مقارنة بسيطة بين أنواع بين ميزات ومساوئ المحطات الأفقية، بالإضافة إلى الميزات الأخرى للمحطات الشاقولية اللي هي داريوس وسافنتوس. هي ليست واسعة الانتشار مثل ما نشوف، محصورة في مناطق محدودة ولها عيوب كثيرة، لذلك الاتجاه يسير حاليا بالاتجاه الفيرتيكال. طبعا الطاقة المحتوات في الرياح هي الحقيقة ممكن تكون طاقة كبيرة تتناسب مع قطر أو مربع القطر للمروحة ومكعب السرعة، لذلك الاتجاه الحالي يتم الاستفادة من هذين الموضوعين، أي الاستفادة من سرعة الرياح قدر الإمكان وزيادة القطر، وزيادة القطر بالإمكان. عم نشوف في أكثر من منطقة للاستفادة من طاقة الرياح. أفضل نموذج اللي هو ممكن نقيسه نحن من خلال عامل الاستطاعة، اللي هو أفضل نموذج الآن عامل الاستطاعة الأوبتيموم القريب تقريبا من الحد المثالي لحدود بيتس، اللي هي تقريبا 0.59 اللي هي ثلاثية الشفرات، تدور عند نسبة سرعة الرياح إلى السرعة المحيطية تقريبا بحدود 7%. إذن هذه المناطق العنفات عادة الريحية تشتغل ضمن مجالين رئيسيين ضمن سرعة الرياح من 2.5 متر على ثانية إلى 16 متر على ثانية، لأسباب اقتصادية. أكثر من هيك ممكن تتحطم العنفة، وأقل من هيك ما بتعطيني أو ما بتأمن الاستطاعة المطلوبة. لو استعرضنا نحن واقع طاقة، أخذنا نموذج في المملكة الأردنية اللي هي الجنوب اللي تبين من خلال قياسنا لسرعة الرياح والمعطيات الموجودة في محطات الأرصاد الجوية، ممكن قسمها عن 3 مناطق رئيسية أغلبها سرعة الرياح تتراوح بين 4 إلى 6 متر على ثانية، ومناطق أخرى واعدة جدا نسبة الرياح فيها تزداد عن 7 متر على ثانية. وهذا دليل على أن أكثر من 60% من مناطق المملكة ممكن ننشئ فيها محطات ريحية سرعة الرياح فيها بين 4 أو بين 3 إلى 6 متر على ثانية. طبعا نحن سوينا استعراض للعديد من المناطق الموجودة في المملكة. حاليا الموجود هو عبارة عن مجموعة أو 4 محطات رئيسية، الطفيلة 117 ميجا، معان فيها 80 ميجا، بالإضافة الإبراهيمية والهوفة هي مناطق قديمة شوية استطاعتها نسبة صغيرة. الآن المخطط له في الأردن في المستقبل القريب جدا سيتم أو حاليا يتم تركيب مجموعة من المحطات، وحدة في الفجيج ووحدة في الراجف، استطاعتهم 89 ميجا و82 ميجا واط. هذه أغلب المناطق الواعدة في المملكة من خلال خريطة الرياح وسرعة الرياح فيها. نحن سوينا قياسات كثيرة على أو استفدنا من مجموعة من القياسات، رسمنا سرعة الرياح، أخذنا المتوسط، أخذنا الاتجاه لفترة زمنية طويلة، اللي تبين تأكيدا على ما سبق بأنه يمكن الاستفادة من طاقة الرياح بشكل كثير كبير في المملكة، ممكن توفر علينا فرص كثيرة. التوصيات الحقيقة اللي فيها أنه طالما الأردن يعتمد بشكل كبير جدا على مصادر الطاقة التقليدية، 97% من استهلاك الطاقة يؤخذ من المصادر التقليدية، لذلك يجب الإسراع في إنشاء محطات توليد الشمسية، بالإضافة إلى عملية الربط المشترك بين محطات الطاقة الشمسية ومحطات الطاقة الريحية. أيضا لا يوجد أي خطر في التشغيل، لأنه خلال 50 سنة الماضية لا يوجد أي آثار. سرعة الرياح ما بتزيد عن 60 كيلو، الطبيعة الجغرافية تسمح، الأرض رخيصة، اليد العاملة رخيصة، بالإضافة إلى توفر الكوادر المؤهلة لتشغيل هذه المحطة. وشكرا لإصغائكم.
Now we will move ahead to our third speaker, Engineer Yaqub Marar, who will speak about renewable energy programs in Jordan. And let me just give you a brief, short biography on Engineer Yaqub. He's the Director of Renewable Energy Department at the Ministry of Energy and Mineral Resources. He has a master's degree in mechanical engineering from the University of Jordan. So, Engineer Yaqub, you have 20 minutes and wish you good luck. Thank you very much.
Thank you. Good afternoon, everybody. First of all, I would like to thank the organizers for giving me the opportunity to update you about our renewable energy program in Jordan. You know, Jordan lacks the conventional resources of energy like oil and gas, but we are really blessed that we have the renewable energy resources, especially the solar and wind energy resources in Jordan. Jordan lies on the solar belt, what is called the solar belt, where the radiation figures are the highest in the world. The solar radiation can reach between 5 to 7 kilowatt-hour per square meter per day for over than 300 sunny days per year. And this is one of the best figures in the world, actually. This can make let's say the investment in solar energy projects in Jordan, especially for photovoltaic cells, PV, to be very feasible and very competitive to the conventional energy projects. And now, actually, it's more feasible than gas projects and even than wind projects for solar PV. The last figure that I have is the 300 megawatt project in Saudi Arabia, where the offer reached 1.79 US cent per kilowatt hour, which is very, very low. We have also wind speeds in Jordan. We have many sites that can reach 7 meters per second of wind speed, which is also very feasible for wind projects. And some special sites, it can reach actually 9 meters per second in Tafila, especially. These are some figures about the energy sector in Jordan for 2016. We highly depend on imported energy. It reached about 95% of our energy is imported. In the previous years, it was 97%. So now we have 2% better than the previous years. It costs us about 7% of our gross domestic product, GDP. The annual growth of energy demand is 7%, and the annual growth of electricity demand is 2.5% for the year 2016. But for the previous years, it was also more than 5%. But due to the low economic growth, actually, this year and in the past year, so the growth of electricity demand have been lowered also. For the electricity sector, the installed capacity of conventional energy projects is about 4,100 megawatts. For renewable energy, the installed capacity was about in 2016 544 megawatts, which is about 13% of the installed capacity. The contribution of the generated electricity from renewables is about 5.6% of generated electricity. Why investment security is high in Jordan, actually, for renewables? Actually, our renewable energy program in Jordan is very successful, and we achieved, or we are going to achieve our targets in the renewable energy strategy. The investors are very interested in investing in renewables in Jordan. Why they do that? First of all, because we have clear development path of the government of Jordan to go for renewable energy projects. We have stable political and regulatory frameworks, adequate and transparent public policies, clear financial and other support schemes like tax regime, tax exemptions, custom exemptions, well-defined infrastructure provisions. We have a good grid to absorb the renewable energy projects. All of this is going to achieve our national energy strategy, which have the goal of to reach 10% of the renewable energy contribution from the energy mix by 2020. This is equivalent actually to 800 megawatt of wind energy projects and 800 megawatt of solar energy projects. We are going to see now how we are going to pass these figures in the coming years. Our regulatory framework for renewables, we have the Renewable Energy and Energy Efficiency Law, which has been published in 2012 and amended in 2014. We have all the, actually this law allows for investing in renewable energy not only through the العطاءات اللي هي tendering for conventional competitive tendering, but also it opened the door for direct proposal submissions for renewable energy projects. We have all the bylaws for renewable energy all issued in the year 2015. We have the ceiling price list for renewable energy technologies also issued by the EMRC, the Energy and Minerals Regulatory Commission. The law opened the door also for the net metering and wheeling scheme, where anybody, all the sectors can install rooftop systems or whatever systems to decrease their consumption of energy by using renewable energy projects or systems. We have a bylaw for the tax exemptions for renewable energy projects and equipment. We established the Renewable Energy and Energy Efficiency Fund, JREF, which has many programs to support the renewable energy and energy efficiency in Jordan by all means. We have programs for grid expansion to reinforce the grid, like the Green Corridor projects in the south, to absorb more renewable energy projects. Now we have in Jordan about 2,400 megawatts of wind and solar PV, photovoltaic cell projects that have been contracted. Out of them, 637 megawatts are already operational now on the grid. The other are under development. The sharing of these projects until this moment, is about 6.5% of the generated electricity. As we said, the development of renewables in Jordan goes through many lines. We have the direct proposal scheme, we have the competitive bidding, we have the EPC turnkey bidding, we have the small-scale renewable energy schemes or net metering. The net metering gave the opportunity to all the consumers to decrease their consumption or even make it zero at the end, so that they don't pay any money for their consumption. Let's have a look about the renewable energy projects in Jordan. We have the operational renewable energy projects. We start with the wind project at Tafila with 117 megawatt. It's through the direct proposal scheme. It's operational since September 2015. We have a 10 megawatt of solar PV project through direct proposal also for Philadelphia Solar, operational since October 2015. We have 2 small projects with total of 5 megawatt capacity through a Spanish grant at Azraq. We have the first round of direct proposal submissions. It is about, the total is 12 projects, solar projects with 200 megawatts of solar PV technology. All of these projects are running now and operational since the year of 2016. We have a project through the Gulf grant. It's on EPC basis. It's 80 megawatt at Ma'an. Actually, it's behind the Al Hussein University in Ma'an. The first phase of this project, 66 megawatt, is operational since September 2016, and the second phase, 40 megawatts, operational since September 2017. We have 13 megawatt at Za'atari camp, 13 megawatt of solar PV. It's through a German grant, operational from last month, October 2017. We have about 212 megawatts of small-scale installed renewable energy systems, or actually solar PV systems, until the moment from all kind of sectors. The total of these operational projects is 637 megawatts. It's equivalent to 6.5% of generated electricity. These are some photos from these operational projects. This is Tafila wind project. This is Philadelphia solar project at Mafraq. This is Azraq small projects. This is Ma'an wind project. One of Ma'an 12 projects, or round 1 projects. This is the Za'atari camp project, solar PV. Now we have the projects which are under construction. We have the 103 megawatt solar PV project at Guera near Aqaba. It's also through the Gulf Grant Abu Dhabi Fund on EPC basis. Now this project is under commissioning actually, so it's in the last stage and will be operational before the end of this year. Maybe this month or next month. Actually, the Guera project is already operational, but under commissioning, under testing. So the COD, the commercial operation date, will be the next month, hopefully. We have the second round of direct proposal submissions for solar PV projects. There are 4 projects, 50 megawatt each, all located in the northeast of Jordan, 3 of them at Mafraq development area, and 1 of them at Safawi. These projects will be operational in 2018. We have 1 wind project of 82 megawatt at Fujez that we talked about. It's through the round 1 of direct proposals. It will be operational in 2018 also. We have another 89 megawatt for KEPCO wind project, Bardo also through round 1, will be operational in 2018. We have the small-scale projects through the net metering and wheeling. Now we have about 180 megawatts under construction. This is the sum, 654 megawatts. This is the Guerra project, which is under commissioning now. We have projects that we signed their agreements, the PPA agreements, power purchase agreement, with the National Electricity Power Company, NEPCO, but they are still under the financial close. They are working on the financial scheme to start construction after that. We have a 200 megawatt for Masdar, it's solar PV. It's a governmental initiative and will be operational in 2019. We have 50 megawatt of wind project through the round 1, also will be operational in 2019 or 20. We have another 2 wind projects through the round 1, 100 megawatt and 45 megawatt, and another 150 megawatt. We have a project through special permission for the generation companies to use renewable energy. So this is one of them, Aqua projects. It's 50 megawatt at Risha. It will be operational in 2019. And we have the AES Mitsui solar PV projects, also 50 megawatt, and will be also operational at 2019. This is the total, 500, 450. Coming projects in the pipeline, we announced actually for the 3rd round of direct proposal submissions, there will be 200 megawatt of solar energy projects and 100 megawatt of wind projects. Now it's under tendering. We announced the qualified companies and signed the memorandum of understanding, MOUs, with them. Now they are preparing their direct proposals. This one will be, this round will be operational in 2020, hopefully. We have a 50 megawatt project for Philadelphia Solar that will be operational in 2019. We have also special permission for the governmental universities to make commercial projects for renewable energy. We expect about, or actually more than 50 megawatt of these projects, and will be operational in 2020. We have a 40 megawatt solar PV projects in South Amman through a German grant, also for the benefit of the communities who hold the Syrian refugees. This will be operational in 2019. We have 200 megawatt of small-scale solar PV systems. We expect that in the coming years. We have 5 megawatt solar PV project at Azraq, also through a European grant under the program RE2. It's on EPC basis, where the owner is the government of Jordan. This will be operational in 2018. We have also, we expect more projects for the electricity generation companies with 50 megawatt until 2020. We announced actually a round of direct proposal submissions for energy storage system. We want, in order to absorb more renewable energy projects and to make to keep the stability of the grid. So we are going to make an energy storage project through the batteries. It will be 30 megawatt for 2 hours. This hopefully will be operational in 2019. Also, there is the other kinds or other technologies of storage are under discussion now, under study. So maybe we will have more technologies for energy storage in the future. We announced also a direct proposal submission for 24 megawatt of waste to energy project at Al-Ikader. It is now under tendering, will be operational in 2022. We have a small project at Azraq, also through a Spanish grant, and it is under tendering, will be operational in 2018. We have all, actually, in Jordan, we have all the templates for to make the contracts, and all the documents are ready, which make it useful for the investors to submit their proposals and to invest in Jordan for renewables. So we have the instructions for developing the renewable energy project. We have the pre-qualification requirements, the power purchase agreement, the land lease agreement, all kinds of agreements are ready. So Jordan has laid down the necessary policy and regulatory framework for renewable energy and is ready to attract and receive commercial investments. Template, contractual documents, PPAs, and instructions for developing renewable energy projects do exist. And grid reinforcement, green corridor, is undergoing by NEPCO in order to install more renewable energy capacities. And also another green corridor is under the study now in the northeast of Jordan. So we are actually leading country in renewables in the MENA region. And I really feel proud whenever there is a conference in the MENA region and I am there. So everybody is looking for Jordan and for its successful program and achievement in this. Thank you.
We can accommodate now 1-2 questions max. The gentleman over there. We have a mic over there.
أنا عارفين. أوكي.
حكيت عن الويست انرجي اللي على الأكيدة، بس كان في مشروع ويست انرجي مع بارك عمان اللي هو كان المفروض إنه يبدوا الشغل ويعملوا له بروجة لازم يخلص من المفروضات نهائية معهم. أنا شو أقدر؟
أنا الحقيقة ما ذكرته لأنه هذا كان من خلال أمانة عمان، يعني ما كان من خلال وزارة الطاقة. حاليا تحت يعني أعلنوا الفائز الأول وحاليا تحت النيغوشيشنز على الأجريمنتس. بعده تحت المفاوضات. لا مش اونلي السعر، لا يعني كان كل الوقت بيعملوا مفاوضات مع أمانة عمان على الاجريمنت معهم، وحاليا بدهم لسه يبداوا المفاوضات مع نيبكو اللي هي مشان اتفاقية شراء الطاقة، لانه بتعرف اتفاقيات تاخذ وقت، يعني مش بسهولة.
We don't have much time, but if it is quick questions, quick answers, please go ahead.
Engineers, here you mentioned some let's say opportunities, let's say promising opportunities about production of different, but maybe PV, solar, or let's say wind energy. What about the hydrostatic plants, thermal plants? Here we have in Jordan plenty of opportunity and challenges in order to improve, let's say, RE market into industry. I mean, you have dams, so you have high mountains, for example, Global mountains or Barma mountains to Dead Sea. So you have, let's say, more or less opportunities. Why are not mentioned here? This is my question.
Which kind of energy? I did not catch that. Which kind of energy? أي نوع?
Hydrostatic, for example.
Hydro. We actually.
Plants, you can use it as well.
Actually, we have 2 small hydro plants in Jordan, about 5 megawatt each, but not more than that. That any project must be feasible to move in it. But we are looking now for the dams for the water energy storage, so that we can have, for example, solar energy and pump the water to the higher level in the day, during the day, and then during the night we can make it again and have energy from it.
Thank you very much.
So it's water energy storage, they call it.
Thank you, Engineer.
Thank you.